although we might get going. So I'll just do a brief acknowledgement of country and then hand over to Matt. We'd like to acknowledge the traditional owners and the land and their custodianship of the lands in which we meet, and pay our respects to their ancestors and descendants who continue cultural and spiritual connections to country, and recognize their valuable contributions to Australian and global society. Thanks everyone for coming, and over to you, Matt.
Thank you very much, Rick. For those that I haven't met, my name is Matthew Greenwood. I'm the Manager of Regional Compilations at the Geological Survey of Queensland, and I'd like to welcome you to our presentation on secondary prospectivity with some of our co-collaborators and partners we've been working with, including SMI and Anita's team at SMI, which we've been working with a long time in the secondary prospectivity. We're really excited to bring this list of presentators to you and share the work that we've been doing with SMI and other partners, as well as they've been doing across Australia in this quite new and developing field. So first, I would like to bring your attention to the GSQ's technical roadshow, which will be up in Mount Isa this year in the 21st and 22nd of August. There will be presentations and also some core viewing facilities available up there. And we'd like to welcome anyone to come and join us up in Mount Isa and hear about the work we've been doing in our new economy minerals initiatives and Queensland Resource Industry Development programs over the last several years. So our first presentator today is Anita Parbhakar-Fox, who leads the SMI MIWATCH team, and she'll be presenting on the work that they've been doing across Queensland and Australia in secondary prospectivity. So Anita, please take it away.
Thank you very much. Can I just check you can see my screen, okay?
We can see your screen, but not your presentation, Anita.
Okay, and that should be good now?
That's perfect, thank you.
All right, thank you very much. So, yeah, thank you very much for having me today. Obviously, it's really a great pleasure to share with you an update on what we've been doing. So I think the last time we gave one of these webinars was in 2021. So in many ways, it's a little bit overdue to be presenting some of the updates we've had across Queensland in the time that's passed. But there's certainly been a lot of exciting developments, which we'll take you through in this very short presentation. So if there's any sort of further questions that you have, please feel free to contact me directly after today. So just to clarify who MIWATCH are, so I think when we gave you the presentation before, I'm not quite sure that we'd formally established. So within SMI, we obviously have 6 centres, but we're located within the BRC, which is obviously the centre from our colleagues that you sometimes hear from, Mark Noppe, who's the director, Nick Cook, Nathan Fox, etc. So within the BRC, we actually have 3 groups, and we're one of those groups within the BRC, in addition to TDK and Deep Mining Geoscience. And so what I'm going to do is I'm just going to spend a little bit of time talking about MIWATCH and where we've come from and where we're going. So, some fast facts here. We were founded in 2021 and currently we're at 16 staff members. We work across the life of mine. So I guess we're all geologists, geoscientists, engineers with a focus on mine waste. And so we recognise there's opportunities across the life of mine to actually embed better practices in terms of applying geometallurgy, mineralogy and new sort of technologies to better characterise these wastes for better environmental outcomes. And so many of our partners are state governments, industry clients and METS partners, and you're going to hear from some of them today in this webinar. And so really what we've delivered is about 50 Stream 1 projects. We've sampled those across Australia. We've certainly seen significant research investment in this area. You'll hear, across the industry right now that there's a lot of startup companies and even sort of mining companies that are really interested in looking at their mine waste as potential resource. So we're really seeing this new kind of industry growing. And so what we've been doing is collecting a lot of information on these mine waste sites, their characteristics, what's the critical element or metal content, what's the mineralogy, what parameters do we need to understand to start making processing decisions? And that's the type of information we've been collecting in these Stream 1 projects. And really what we're delivering to the industry is these pre-competitive data reports. And so many of these are now sort of starting to become published, and certainly with the Northern Territories, we have some reports there. Geoscience Australia are about to release some, as is New South Wales. And indeed, Queensland have got a number of those already on their portal. So they're really repositories of information to help you understand what's at these sites and what the opportunities could be. And so, I must acknowledge the efforts of the MIWATCH team. So certainly we've had lots of members that have, joined the team and since, sought other opportunities. And I must acknowledge the efforts of those people as well. But certainly what you can see here is a very strong cohort of geologists, technicians, metallurgists, etc. And we're really, looking to sort of, whilst we've spent the last little while characterising these sites, certainly what we're looking to in the future is now to start embedding practices that really extract those metals from those materials. So we're certainly looking at bringing on new geometallurgists in the future who are going to be really instrumental in driving that metal extraction piece. So that's who we are. And thank you so much to all of the team for their hard efforts in characterising Australia's waste. And so really our mission statement is to apply geomet tools to enable geoenvironmental characterisation across the life of mine. So we work in 3 thematic areas. And the one I'm going to talk about the first is theme 3, where we're characterising existing mine waste materials to really determine what the reuse opportunities could be. And so really the motivator for this type of research has been the critical minerals strategy. I mean, right now, today in Brisbane CBD, there's a conference focused again on critical minerals and the opportunities that presents to Australia. And indeed, we're seeing that conversation extend to mine waste. I mean, mine waste has been included in this strategy, in the batteries strategy. Internationally, it's really a growing area of opportunity because we all recognise that contained in these mine waste materials are a whole host of critical metals that we need for the energy transition. And so what we've been doing, our team, is going across Australia, and I've showed this map lots of times and I'll probably keep showing it, but really it does articulate the scale of the opportunity. We can see across Australia, once reported 50,000 mine sites to go and explore. And, for us as geoscientists, it's great because if we look at the diversity of these mine waste sites, no 2 sites are the same. So what we need to do, and what MIWATCH have done, is develop methodologies, sampling methodologies, characterisation methodologies to actually help us collect samples at these sites and actually understand what's there in terms of that critical metal potential. So it's certainly a very interesting space to work in. And indeed, the circular economy has been a massive driver for the type of work we've been doing as well. So there's lots of reasons why characterising waste, reducing that environmental footprint, engaging in economic rehabilitation is a very good idea. And so, within the Theme 3 programme, we actually have 3 streams of work. We have Stream 1, Stream 2 and Stream 3. And Stream 1 is really what I'm going to focus on talking about, which, it's our first pass investigation of mine waste characterisation. So what we've developed is a very kind of unique and bespoke characterisation programme. We integrate chemical assay, mineralogy and mineral chemistry characteristics into the programme. And based on that information that we collect and the way in which we process and evaluate that data, we can actually make an assessment if there is critical metal fertility, and if there is, which mineral processing methodologies are best suited to recover that value. And so that's what a Stream 1 programme delivers. And if we look at where we've sampled across the country, you can certainly see that MIWATCH have been very busy. So if you follow our blog, we've been a bit quiet of late because now we've actually been in a process of sitting down and writing up a lot of these reports. But, across all the different states, we've had the opportunity to work with state government partners, and we've very much valued the time and the effort and the collaborations with each of those partners. And indeed, we've had the opportunity to do some direct one-on-one projects with industry partners to actually sample and characterise that waste to look for critical metal resources. And so, in Queensland, what have we done? Well, we've certainly been busy there. That's where the lion's share of our Stream 1 programmes have been. And there we've sampled a whole diversity of waste and tailings materials. And you're just looking at a snapshot there. I didn't quite get to updating all of it properly. And to be honest, there wouldn't have been the space to actually do that because there's so many sites to name now. But certainly you can see that, it's not just tailings that we sample. I think sometimes when people think about mine waste, they kind of hone in on just tailings. But there's slag, there's waste rock, there's spent heat leach materials, and indeed, a growing body of interest in coal mine waste and coal ashes and so forth. So there's a lot of different things that we've sampled. There are some things we haven't sampled, such as bauxite residues. And I think as we move into the future, that's probably something that we do need to sort of, take a bit of a focus on. But certainly a lot out there, a lot we've sampled, and we have sampling methodologies to do all of that. So I'm going to just step through some of the early results. I know that cobalt, when we sort of kicked off this programme, cobalt was the main thing that people were interested in. And so what I'm sharing is, I guess, some of the national data from the assay campaign of cobalt values across the country. Now, I'm not allowed to include New South Wales just yet. That data is under embargo until possibly September. But what you're looking at is that in terms of where our cobalt resources are in waste, we can certainly see in the Northern Territories at the Pico mine, there's a very high hit for cobalt there, but certainly in the Northwest Minerals Province as well. And as I said, when we started off this program, that was, I guess our focus was on cobalt in the Northwest Minerals Province. And we certainly have evidence to show that there is significant endowment in the wastes there. And if we dig into that a little bit further, what we can see is that we do have endowment at sites like Osborne, Great Australia, Kurridala, and Rocklands. Now, these are sites where we've done additional test work. And if I flip to the next slide, certainly at Rocklands, we've been there, we've characterised the tailings very thoroughly. And working with our Japanese partners, Geochemical, they've actually developed a new flotation methodology to recover that pyrite, because it's cobalt hosted in pyrite, and actually start to recover some of that cobalt and that copper. And you'll be hearing from a presentation from Rech from Geochemical a little bit later on, who will talk to the details of that particular program. At the Osborne mine, again, partnering with Cobalt Blue, we've done a trial. We again had sort of cobalt hosted in pyrite, and using their proprietary technology, we've done bulk trials to see if we can recover that value. And certainly there have been some very promising results for that technology, which, is something to be considered in the future in further test work programs that we're going to run. And certainly at Pindora, there we saw cobalt hosted in a range of iron oxides and indeed some other oxide materials as well. So working with a company in South Australia, in Iveco, using their resin technology, we've been looking at new ways to sort of recover the cobalt from those materials with very successful results, again, proven. So I guess what we're seeing is, the opportunities to recover these potential critical metals from these materials really does need us to sort of look at new innovative technologies and methodologies to actually crack out that value. And it's, seeing that whole spate of, refined mineral processing methodologies pop up has been really key to actually unlocking the value from these sites. Now, you're going to hear from Loren Nicholls in a little while, and certainly you heard from her in 2001. I'm working on her PhD study. She's, taking the characteristics of cobalt in her materials. She's actually been able to undertake some metallurgical test work too. So I don't think she's going to be able to talk about that in her presentation, but certainly it goes to show you where this sort of type of research is leading. So we characterise the stream and we identify the value. The PhD students like Loren, they do a lot of detailed test work at particular sites. And then again, we can sort of engage with third parties and indeed our own metallurgy team within UQ at SMI, at the JKMRC, to actually see if we can recover that value. So it's a really exciting space to be in. Now, another metal that's certainly been very interesting of late is indium. And I think it's one that certainly GA, CSR and others have become very interested in, because as Olivia Mejias will tell you later, it's very important and pivotal in a lot of these technologies we need for the energy transition. And again, looking at our national mapping, but excluding New South Wales, the assay campaign, the average PPM values show us that nationally, our sort of deposits of indium in waste certainly lie in the Northeast Minerals Province in Queensland. And again, if we drill into that a bit further, we can see that the lion's share is indeed at Balgammon, Herberton, and Jumna. Now, I guess in Olivia's PhD research, we wanted to sort of compare and contrast indium signatures in a couple of different ore deposit types. So Olivia will be talking about her research at Balgammon and Mount Morgan, where she's done a very deep dive in terms of characterising, where the indium's hosted in the different sulfides. And what that's really helped us do is sort of understand what mineral processing methodologies could be useful to actually concentrate and recover that metal. But, we have to think about practical mining. So what would this actually look like? If we've identified the rocks that contain, the indium-bearing minerals, how exactly will we go back to a site like Balgammon and recover that value? And so what you're looking at there is some of the PAF cells, or the potentially acid-forming cells at Balgammon, and these are obviously waste rock materials. And so we need to have technologies and methodologies that help us do that waste rock sorting. And so we've been doing some work with Gavin Rech down at TOMRA, where we've actually been doing some trials on the Balgammon rocks, and he'll be presenting an update on that shortly in this webinar. So we do have to think, now we've characterised it, what does the practical engineering work look like to actually concentrate, sort, and separate these materials? And when we think about separation too, there's other technologies that are going to help us unlock the value. So certainly working with Daniel Lay here at the JKMRC, which is part of the SMI, they've got this new technology, high voltage pulse, or HVP, which, has certainly crashed onto the scene in a very popular format. That just a couple of weeks ago, there was, a media blast about this technology, which was very well received. But certainly they've been working hard for many years to optimize this technology to separate gangue and non-sulfide gangue materials. So now was a logical time for us to go to their team with our waste rock materials and, start to explore how we could actually sort and pre-concentrate these waste materials, so then we can make con, which we can then take through to flotation, and then eventually, potentially into hydromet sort of labs. And what you're looking at here is obviously our colleague Hong Peng in the hydrometallurgy group. And certainly what their group have been doing is looking at how, once we've got the concentrate, the sulfide concentrate, or the critical mineral concentrate, how can we actually recover the metals from those materials? And their team have been working very hard looking at cobalt and other metals, and he'll be providing an update on that research a little bit later on this afternoon. So I guess the point is there's no point in characterising where these materials are unless we're going to take it through to that mineral processing and metal extraction steps, which we've been working very hard to do across the University of Queensland. So I just wanted to share a couple of final slides in this particular segment. Vanadium's a metal of extreme interest here in Queensland, and certainly it's one that we've looked at in our 48 element assay campaign. And what we see in terms of, do we have significant endowment above crustal abundance? Well, sadly, no. The majority of our materials certainly don't really sort of sing in terms of being endowed in vanadium. But what was interesting in caught my eye was actually, if you look at our data set, where some of our big hits actually sit, is actually in the coal ash waste. So, where we've got Swanbank, we sampled the coal ash dams there, just sort of proximal to Brisbane. And we just saw significant endowment of vanadium in those materials. So I guess as we sort of start to go back and evaluate, not just metal mining wastes, but coal ash dams and coal wastes, there is that potential for vanadium in those materials. So something to think about. And I know certainly rare earth elements are a hot topic nationally, if not within Mount Isa. Where does the value sit there? So if we look at the light rare earth elements, we can certainly see that we have a major endowment in Mary Kay, which we all know about and we've already talked about in this sort of forum, in this context. And indeed, that metal extraction work has been undertaken within UQ and with different partners in SMI and others to really look at if we can recover that from those Mary Kay tailings and indeed waste rock materials. And indeed, there have been some significant findings from that research too. And then if we think about heavy rare earth elements, this one surprised me. So Kuridala, we see quite an endowment of dysprosium in the slag materials that we collected there. So I guess it pays to sample everything and to have a good look at what the endowment is, because potentially coupled with some of the gold sniffs that we got in Kuridala, there could be the opportunity for multi-commodity recovery from that particular waste. So I guess where's all this going? I mean, we've done a lot of characterization work. Well, the work and the data that MIWATCH are generating is intended to go into the Atlas of Australian Mine Waste. And so, RMIT and Geoscience Australia and ourselves working together collaboratively, this is the version 1 of the Atlas that's been published. And version 2 and later versions will indeed house the chemistry, the assay data, potentially the mineralogy data that we've collected through the MIWATCH program. So watch this space for that. And what that means is there's an opportunity to deliver pre-competitive data for investors seeking to invest in critical metal waste sites in Australia. But for us as academics, it gives us the opportunity to generate new knowledge of Australian ore deposit waste signatures. And that potentially could be a desktop resource to help others in other countries actually explore and understand what could potentially be in their mine waste materials too. And so, just as a very quick, summary of where we're seeing value, we've only just started our campaign in WA, a couple of sites there, and we hope there's going to be many more to come. But, that's just kind of summarising where we see the value. So Northern Territories, cobalt, not listed there actually, but antimony, rare earth elements, also rare earth elements seeing Port Pirie down in South Australia, but certainly the lion's share of a lot of the interesting things do seem to be in Queensland. So it's great that we've had the opportunity to characterise a lot of things, because certainly characterising mine waste, it's not a cost. It should never be seen as a cost to a business. It's a strategic investment, and it will give us the edge in terms of thinking about what future opportunities could be, but only if they pair with the right technologies to recover the critical metals. And so I shared with you some of the technology partners we're working with, both internally and externally to UQ. But certainly there's a lot more opportunities out there, and through Trailblazer and other schemes like that, there's an opportunity to really explore what those other new technologies could be. And certainly they're things that we've summarised in previous publications. Now, in the final minutes that I have, just want to touch on theme 1. So I said we worked across 3 thematic areas. Spent a little bit of time talking about, how we characterise and think about existing waste materials, but surely the opportunity is to focus on future mining materials. If we really want to sort of significantly reduce our future waste footprints, which we absolutely must according to the Secretary General, then what we need to do is characterise our waste materials up front as we sort of identify new ore deposits. And certainly there's a big push now to sort of find new deposits of critical metals, which means we need to thoroughly characterise all of that drill core material to actually understand what the potential, waste characteristics could be. Because if we don't, Antonio's completely right there. We're going to leave a toxic cloud, we're going to leave pollution, and we simply cannot repeat the mistakes of the past. Now, we have the opportunity not to repeat those mistakes. I mean, if we take a step back and look at something like acid mine drainage, which is possibly the worst thing associated with mine waste materials if they're not managed correctly, we've got to innovate. I mean, looking back in time, how have we predicted AMD? I mean, up until sort of the 70s, it was very sort of, based on qualitative observations. But after, 1977, we started using geochemical tests. And indeed, they were developed for the coal industry. So are they appropriate for the metalliferous industry? Possibly not, considering the complexity of mineralogy that we're sort of dealing with in these potential deposits. We've relied on geochemical testing methods since 77, but really, we need to be looking at how we can better embed technology to help us predict AMD more appropriately so we can avoid making the mistakes of the past as we develop new ore deposits. So what we need to do is we need to use these drill core data sets that we know companies are producing. So we know, many companies out there, state governments, etc., they're collecting kilometers of hyperspectral data. And they are asking the questions, how can we extract more information from these data sets? And certainly, the team MIWATCH and other collaborators, we've been developing a whole set of, indices that can actually be used to take this data and do environmental forecasting to mitigate the impacts of AMD, or to, help us design better our waste repositories so we can avoid producing AMD. And certainly, this has been research that's been funded by various mining companies and indeed the Queensland government. And what you'll be hearing from Enrique a little bit later on is the work we've been doing in that space to really get ahead of the problem before it actually is. And indeed, there's lots of technologies that could be used. And certainly in a recent edition of Elements magazine in December 2023, with a tech collaborator, Regina Baumgartner, who's one of Enrique's PhD supervisors, we actually, had to look at all of these different technologies and sort of reorganized how we can actually better use them to improve AMD prediction. So we can potentially avoid making the mistakes of the past as we mine for new deposits. But really, the holy grail would be to actually fully characterize these materials and understand how we can significantly reduce our waste footprint by finding, additional commodities that could be recovered. So by using all of these data that we're now generating, hyperspectral, LIBS, tornado data, all the things that, the GSQ team are very well versed at, we take this data, we build these data stacks, and we can actually start to model what additional commodities could be recovered from these. We need to redesign those flow sheets to, see if we can, pull out industrial materials. And maybe we can even, find minerals for other industries, ethical cosmetics, for example. But fundamentally, across both theme 1 and theme 3, mineralogy is the key to net zero mine waste. I mean, existing mine waste, future mine waste, we need to actually understand the components of that waste to make better decisions about their outcomes. And certainly that's something we've seen with our All Sands group here at UQ, at SMI, specifically led by Daniel Franks. So they've obviously been very successful in terms of thinking about, the opportunity for sand co-production early stages. If you characterize it, you build it into the flow sheet, then you have that opportunity to significantly reduce the footprint of the waste materials at the end of life of mine. So smarter characterization, smarter outcomes. So I guess, what are the next steps for MIWATCH? We've got lots of things that we need to do in terms of, embedding geophysics into our characterization. If we can actually get a sense of what a mine waste environment site looks like before we go out and sample it in theme 3, then we've got a better opportunity to recover, things like representative samples. If we can do more things in field, and we've had some chats with Index about the blast log, more in-field measurements can indeed also help us better understand the subsurface of these mine waste site environments. And certainly I've said mineralogy is the key, but as we're dealing with challenging mineralogy, as Loren and Olivia will show you, we need to actually pivot to, using different and more advanced mineralogical tools, but we also need to find a way to make them more accessible to, with the data processing and so forth. And when we do see that opportunity to, recover the value, we need to use modular technologies for more in-field processing. And I'm sure Gavin's going to share with you an example of what that vision could look like from TOMRA. And so just as a very final plug, I have to say the Queensland State Government have, really shown a lot of leadership in this space. And it's been great to see recently the announcement of the, the $5 million fund also to actually drive explorers to actually explore these mine waste sites. So, well done Queensland on that leadership. And it's great also to see the federal government taking interest in actually supporting Queensland operators to, recover value from their waste. So $2.2 million to Evolution Mining to retrieve cobalt from the mine waste. So we can see it's not just something that we're doing here in our labs or here in an academic environment. It's actually influencing industry, and it's getting into government radars. And I think slowly, we're going to see this, this sector of mine waste business, or this business sector that's growing mine waste to re-commercialise, grow exponentially, which, was the flavour that we got at the recent Australian Mine Waste Symposium. So that's a very quick snapshot of what's been going on here. And if you want to really unpack this talk, I think, download it and slow it down half speed. And then, maybe you can actually separate the spacing between my words. Apologies for talking fast. But yeah, certainly thank you for listening. It's going to be a great afternoon ahead. I hope I've given you a flavour for what's coming. And I just want to say, finally, a big thanks to Cam Bawani, who's in this photo here. So she was one of our MIWATCH members who sought a new adventure in WA last week, and so we just want to thank her for all of her efforts, her help in sampling across the country, and we wish her well in her new role. So thank you very much. That's enough from me.
Thank you so much, Anita. Obviously, so much to go through in short time, so you did a great job keeping quite close to time. So thank you for that. We do have the Q&A box down the bottom, so if people do have questions for Anita or any of our presenters, if you put in the Q&A box, the presenters can answer it live, or if you have a question that sort of comes up later, put in the Q&A box and we can ask our presenters to follow that up and provide a response via text. But we are running a little bit over time already, so we might go straight to Olivia, who's going to talk about geochem modelling of indium in aqueous mine waste environments. Thanks, Olivia. I think you're on mute, Olivia, but we can see your screen.
Sorry, can you hear me and see my screen now?
Yes, yeah. And yes, well done.
Okay, thank you. Okay, good afternoon, everyone. Thank you so much for the opportunity to present today. I'm very excited to show you several new things related to indium in my waste today. So first, as a very quick introduction, we know, right, tailings and waste rock maybe are the more common mine waste sources for critical minerals right now, but as Anita mentioned, there is several other type of mine waste, slags or dust, for example. But also in the last years has been a little bit more focused in aqueous sources as well. Let me just 1 second to use my laser point. So for example, this article was released just a few months ago for a US team, very focused only in critical minerals recovery strategies from aqueous sources. So you can see, for example, in the case indium, gallium, germanium is not established yet. So there is opportunity to investigate more and define if more critical minerals could be supplied this chain, right? So, but most of these elements, or for example, indium, gallium, germanium, is byproduct, right? So most of the focus on extracting elements from waste is more in the middle of this wheel or main metals, but we have a huge opportunity to looking for more option as a byproduct, as I mentioned, aqueous sources and solid sources. So in terms of indium, and based on that information and any critical minerals, always is important to know how much we have in our mine waste, and most of the time we compare with crustal abundance, right? As we can see here in terms of indium, and to know what is expected in natural environment, even solid on aqueous environment, what should be expected of indium or any critical minerals when it's not affected by anthropological work. But in terms of water, it's very not so clear for all the elements. How I can compare how much indium or any critical minerals I have in my mine waters or mining industry impacted waters, right? So in that case, for indium, we have to compile available information and to set up a background. So could be happen for several critical minerals, has been no focus in the last decades. So in the case of indium, could be more than 10,000 times higher in waste rock, and several, even 100,000 times higher in water impacted by smelting. So we have now a very snapshot, right, about how much indium is expected in natural environment, in mining environment, but also what is the connection with our deposits. So This graph is just a summary of sphalerite data, but we can see in the right side of the histogram how granite-related porphyry and some xenotherma should be expected more ore deposits really high in indium. That should be expected as well, the mine waste related. So based on that and what Anita mentioned, in Queensland, we have two targets in this project, PhD project, Balgamon and Mount Morgan. So Mount Morgan is a volcanic massive deposit, and in this case, we include solid and aqueous samples, right? So we include waste rock, precipitate, and sediment, and in terms of water, water from seepage, open pit, and from the stream, that in this case is the river, trying to include from the surrounding the mine site, but also upstream and downstream. And the same methodology for Balgamon. This is a granite-related deposit. The current status is an abandoned mine, and it was declared as a worldwide indium resources time ago. So in this case, because it's a smaller mine site, we cover with 45 samples, solid sample, and again, the same methodology to include water sample from the closer stream. In this case, it's Jamie Creek, and water from the mine site. So the idea before going into the geochemical model of indium in water or low temperature system, the idea is to show you what is the main key result in terms of the solid, because we need to understand what is the minerals that host indium and then release into the solution to do a better model. So in this case, all these samples that you already mentioned, waste rock, sediment, precipitate, and water, we also include some drill core samples to compare against what should be expected in related to indium when it's no weathering condition affected. And most of them ran through a multi-scale characterization from micro scale going through meso, micro, and even nanoscale when was feasible for the sample. For example, very porous sample as sediment or precipitate, very complex, trying to do the sample preparation. So it was possible for ore and waste rock. And in the case of water sample, it was a complement with a geochemical model to understand indium speciation, saturation index, reaction, Pull-Beck's diagram, and finally a reactive transport model of indium in one dimension. So how all these two information, right, we can understand better indium and in the indium cycling in mine waste environment, but use to develop recovery strategies. So as a very quick in terms of bulk, we can see already how Balgamon is so much rich in terms of indium, about 1,000 times higher in comparison to the crustal abundance, and Mount Morgan is just 10 times higher. Even though this huge difference, and we can define as an indium rich system waste system versus a poor indium waste system, is very interesting to see the correlation. So even though the quantity of indium, we can see positive correlation with indium in both systems with copper, silver, and cadmium. But also in Balgamon, tin and zinc and bismuth has a role in this association. Now, for example, this is one of the waste rock sample from Balgamon that we ran using the Ecor LIBS. It's one of the latest model that LIBS released in the last years. So we can see this is a sample like at 20 centimeters, and we can see a really high resolution. This is a 50 micron spot size of the laser, and the time that get this, the process, I mean, it could be around 5 minutes. It's very quick and good resolution and not so expensive as other techniques. And in terms of indium, that is very challenged. And also I know other critical minerals in terms of overlap. So for example, indium overlap with tin, and this is a tin mine. So it's very challenged to characterize indium if you are not very careful about that. So in the case of LIBS, the peak of tin and the peak of indium are no overlap. So it's really good in terms of identify the distribution of indium, but the cons is a semi-quantitative technique, but we are working to move to a calibration and get the quantification. But it's very interesting to see the indium distribution in this waste rock sample. Sorry. Now if we use another technique a little bit more in the micro scale, using the last technology released by Thermo Fisher, MAPS Mineralogy, more than show you the minerals identified as indium-bearing minerals, is maybe this is not the last image, but the good thing, we are also working in the solid solution, for example, estanite, kesterite, and the intermediate product in the distribution. But also it's very interesting to see the distribution using heat map of indium, and it's very clear how it's high concentrate in grain boundaries. And so should be very tiny stanite, kesterite, and intermediate product minerals that preference concentrate or segregate in between of these big sulfide grains as sphalerite or chalcopyrite, for example. So now we have already a little bit more information about the textures, right? Some minerals. So now we have the two deposits here to compare the concentration of indium in the main minerals. So for example, Valgaemon and Mount Morgan both contain concentration of indium in chalcopyrite and sphalerite. But if we compare the levels, in the case of Valgaemon, is about 1000 ppm, and Mount Morgan is up to 100 ppm. So difference is very huge. And also the association. So in the case of Valgaemon, as I mentioned, we have this estanite, kesterite, cassiterite. So the association makes also a huge difference in terms of indium content. And in terms of texture, we can not only confirm the micro-inclusion here, these little grains with yellow with high indium, but also zonation that is very interesting. This is a cassiterite, so it's a zonation of indium at the edge of the grain. We can also confirm exsolution in the chalcopyrite, very high with indium. And in the case of sphalerite, you can see it's very smooth, the yellow color, but also I will show you another technique that we can confirm that indium not only is a solid solution in sphalerite, it's also segregation at nanoscale. So talking about nanoscale, it was possible to run several samples, more focused on the ore than the waste rock. This is a waste rock sample. So we can see here one of the needle of a sphalerite sample, and all the purple color represent indium distribution. So we can see how is indium very smooth, and it's part of the solid solution substitution of the sphalerite. But here, and I can try to press the video. I don't know if you can see the video. Yeah. You can see the grain boundary of sphalerite is a more concentration of these features, very elongated feature that could concentrate even about 10% of indium. So we can confirm not only solid solution, but also specific features that preference this location in terms of mechanic to concentrate trace element as indium. So now if we understand already the minerals, primary minerals, right, the concentration of indium, and we need to model how indium is released from these minerals, a good first step is to understand what happened with the dissolution of this mineral. What should be expected to dissolve faster than others, which should be the secondary minerals that would be controlled and concentrate indium as well. So here is a good example of a waste rock that is very sulfidic in the left, and we have the goethite formation of the rim in the right. So if we overlap another techniques, for example, synchrotron, and we use the main composition of these indium-bearing minerals, we have a sphalerite here that we run laser ablation, chalcopyrite, confirming the 1000 ppm of indium, less indium, but a high volume of very reactive pyrrhotite. It's very easy to dissolve this pyrrhotite, and then arsenopyrite. But also we have this zinc distribution that is granite, so we can confirm that is some formation of this spinel mineral that also concentrate indium and goethite with indium. This is a few of example with secondary minerals we found so far that could be show the control transport of indium when the main mineral start to alterate, dissolve, and release indium into the system. So then another example focus on the sediment and try to understand when indium is released is this stalactite, what we also found in Valgaemon. It's very rich in indium. So far, I've never seen an article focused on secondary minerals that can contain about 100 ppm of indium. So if we use synchrotron, again with the main concentration of element, we can see it's very high in arsenic, iron, and copper as well, not only indium, also vanadium. And if we try to do a zoom, we can see very interesting textures. And then if we overlap with the SEM, we can confirm very clear the interground between all these several microorganisms that grow with this or trap this old element as iron, copper, arsenic, and even indium. So it's very interesting because could be very high potential in terms of biomining or bioremediation. This is another picture of the same stalactite. So we can see all these microorganism textures. This is very impressive as well. We can see part of the original rock, very round shape, the transportation between the pile to where we found this stalactite. I will show you, it's not so far. So this shape is by microorganisms as well. So we ran and we took, of course, some DNA samples to get the identification. So we can find bacteria from Firmicutes phylum, and also from Chloroflexi and culture, and also bacteria not classified. But beyond going to bacteria by bacteria name, the important things is maybe this type of bacteria could be tolerate very well high concentration of element, including critical minerals as indium or vanadium that was very high if we compare with the ore or the waste rock, for example. And also very interesting that several bacteria, what we found is unclassified or uncultured, so also could be very potential for more microbiology approach, maybe identify if could be new bacteria that tolerate better critical metals concentration. So now if we have all this information right about ore, waste rock, sediment, precipitate, what happened with the water, and how all this information will be input for our model. So Mount Morgan, we have here the distribution of indium and Valgaemon. Again, as we expected, is less indium in the Mount Morgan waters in comparison to Valgaemon. However, we can see similar correlation in both deposits. So pH as the main control, very acidic, more indium, positive correlation with chloride, fluoride, arsenic, lead, and iron. So that is very interesting. But what does mean in the model? So when we move to the model, we use the FreeQC software. And beyond the input that we already have from the samples, we need a database. That is a library that contains the thermodynamic data of the element that you want to model. So as is very common with critical minerals, because it has been a real focus in the last decades, is not about libraries in mineralogy. It's also libraries related to thermodynamic. So for example, the only available thermodynamic for indium after review several libraries was only this one. So the idea was to create and modify a library and include all the thermodynamic data of indium with different type of ligand from literature review and update the library, and then create our own library that is useful for indium. Then the mineralogy, the same, these libraries contain mineralogy that is assumed as a pure mineral phase, not as a mineral that contains trace elements. Some from the laser ablation and microproof. We recreate the empirical formula, so sphalerite, chalcopyrite, and pyrrhotite that contain trace element, and the reactions simulate the acidic environment, or the acid mine drainage. And the other input that we check, it was the topography. So for example, how can I see the video here? 1 second. Here. So for example, the topography was checked and tried to mimic the physics involved in terms of the altitude and the difference between this path waste rock going through the open pit and finish in the Jamie Creek. So that was important before to start to model. So as the result, and this is very exciting to show, we can have the distribution of indium with all the complex from the library. And this is a real sample from fieldwork from an acid mine drainage. So we can confirm that indium is free in very acidic condition below 2.5, but in between 2.5 to 4 is a really high competition with sulfide complex and a little bit less with fluoride and chloride. And the Purbeck's diagram were also created using this software, and we can confirm different stabilities system. So I'm almost in the last slide. So the saturation index was also part of the model, so we can confirm in acid mine drainage the presence of jarosite, germanite, and natrojarosite that also we found in XRD, so could be a controlled transport of indium as a dissolved mineral genlandite, that is an indium mineral, and gypsum. So as this last step that we are still working with CSIRO and in the numerical modeling team with Dr. Thomas Poulet and Dr. Poria Benov-Darfar is try to include more information related to the topography that is not possible with geochemical software as FreeQC or any similar software. So we need to couple and include more information about the hydraulic driver in terms of how the altitude and the different topography could be affect our model. But so far we can see the correlation between pH very acidic going to equilibrium over time and the release of indium when this pH is acidic and going to zero over time. So far we can confirm that indium is a mobile element with a specific control condition, follow a specific element, but tin, zinc, and iron play an important role. The association of mineral as well to make an indium-rich mine waste deposit. The occurrence or distribution is very variability from micro to nanoscale. The dissolution rate, we can expect some release of indium faster from specific minerals. And the mobility, as we confirm the pH specific control below pH 2.5 and in between should be a competition between sulfate and hydroxide complex. And the microbiology, I think, is a really interesting insight, not only in terms of cycling and transport of indium in waste system, also as a potential biomining or bioremediation opportunity to explore in depth. So thank you so much always to the supervisory team, and all the team has been involved in this project, and this presentation in particular more focused on the model with a numerical modeling team with CSIRO. So thank you so much.
Thank you, Olivia. Again, we're just a little bit over time, so if you do have questions for Olivia, please put them in the Q&A, and she'll be able to answer them in text while Loren is presenting. So our next presenter is Loren Nicholls, who's going to talk about deportment of critical minerals in mine waste, chasing cobalt. Go ahead, Loren.
Hi. All right, can you see my screen?
We can see a screen, but not the screen you want to share.
Oh,
There we go. Perfect.
how's that one?
That's much better.
All righty, brilliant. Okay, hi everyone, and thank you so much for attending today. I am going to be talking a little bit about cobalt deportment and why this is so important to understand when we're building really appropriate mineral processing flow sheets. So yes, the PhD that I'm working on at the moment, and hang on a second. Oh, there we go. Right, it's all working now. The PhD that I'm working on, and I'm about to finish in September actually, is on the geometallurgical characterization of mine waste, in particular looking at cobalt in copper mine waste. It is working with Anita, with the MIWATCH team, and it's also funded by the Department of Resources and GSQ under their NEMI package. So in terms of the bigger picture, I mean, mine waste, we all know it's a really big problem. We've got global tailings of 282.5 billion tons. And when you put this into context with the rest of, you know, Queensland and Brisbane, because we all know Suncorp Stadium, which has a capacity of 52,000 people, but you can actually fill this stadium over 126,000 times with the mine waste that we have around the world. So it is a big problem, and as we're moving into this era of ESG and sustainability and circular economy, we need to figure out ways to manage it better. Now, the majority of the tailings are actually produced from copper mining, 46%. But the cool thing about copper is that it's associated with a lot of other companion elements that are often rejected to the tailings stream because they're associated with pyrite, for example. And some of these elements are critical and strategic minerals that sit on Australia's list and the list of the rest of the world, which is pretty cool. But the one that we're going to focus on today is cobalt. Now, I am pretty sure we all know the risks associated with cobalt and why it's a critical mineral, but the demand is outpacing supply. It's obviously very important in battery technology and electric vehicles. And our supply chain is really reliant upon the DRC and China. But Australia does have an opportunity in this space. And particularly if we look at Queensland, we have a lot of copper mines in Queensland, and many of these are actually associated with cobalt mineralisation. Particularly in the Northwest Queensland Minerals Province, there are 29 copper mines within a 320-kilometre distance between each other, which sort of leads me to think about, and the Queensland government to think about, you know, what about a centralised reprocessing facility for cobalt to build secondary cobalt resources in Queensland, to establish that industry and to really, you know, lead in circular economy and critical mineral production from secondary resources around the world. But in order to be able to do that, we need to understand where the cobalt is and how it is hosted and how we're going to be able to get it out. And that's where geometallurgical characterization comes in. It's multi-scale, as Olivia was talking about. We start with sampling the actual tailings material, then move down to look at the mineralogy, down to the particle characteristics, how this will impact its recovery, the geochemistry, and eventually the deportment of the particular element of interest within those different minerals. And so I'm just going to take you through a case study, which is part of my PhD, to explain how I've used this geometallurgical characterization approach. Now, I'll just put this on mute. So the first thing that we did was we sampled the tailings dam, and we did a systematic grid sampling to be able to get representative samples of this tailings dam. And a massive shout out to Matt's team, Roger, Dom and Kate from GSQ, who came out with me for 2 weeks in Queensland and drilled 26 hand auger holes down to 10 meters depth. You can see here, it was quite a show. Thank you very much, guys. But the initial understanding that we started to pick up of variability in this environment were the variable efflorescent salts that we were beginning to see on the surface. And so this starts to make us think about cobalt mobility, about metal mobility in general in these environments, and where it might be hosted. So this heterogeneity was expanded as we looked at the actual tailing samples that we had. So here are different facies that we found within those samples across the dam, and there are 12 facies. You can see here there's an enormous amount of variable mineralogy, oxidation state, texture, grain size, and there's also variability in the cobalt distribution within these different facies. And you can look in the downhole chemistry. I've just got an example there. Cobalt is depleted at surface, but it is enriched as we get deeper down, and that's partly because cobalt is really mobile in acidic fluids. When you have pyrite and it oxidizes, it forms sulfuric acid, cobalt becomes mobilized and then reprecipitates below the redox boundary. So then let's look at this BSE image of the SEM, and you can start to see this heterogeneity in these tailings. We've got lots of different mineralogy. Here you have some quartz, you've got feldspar, you've got pyrites, different sulfides as well. There's iron oxides, and there's also clays and sulfates that rim these gangue mineralogy that go into the tailings dam. You also have really variable grain sizes. So we've got from 8 to 280 microns here, and they also get often sourced from many different sources of mine waste and different projects that get deposited into big tailings dams. So we need to be able to sift through all of this and understand where our cobalt is sitting and what we need to target to be able to recover it. And what we did was we used automated mineralogy in XRD and identified the average modal mineralogy is dominated by quartz, pyrite, and feldspars. We did have very, very trace amounts of cobalt sulfides and cobalt oxides, but not too much. So when you start to look at the cobalt host minerals, the specific cobalt hosted sulfides, such as cobaltite, alklasite, and carolite, you know, we had 0.05%. There wasn't a real lot of it. There were also some sulfates, some oxides, and carbonaceous material. So I then did some back calculation using mineral chemistry and the modal mineral abundances, and identified that of those 0.05% of cobalt sulfides, 9% of the cobalt contribution to the assay was from the cobalt sulfides. And I've got some examples down the side there. You can see they're very small grains down to 10 microns. 18% was contributed by the oxides and sulfates that we were actually able to observe in MLA data. So here's an example. It's a big grain. They're agglomerates. But then we had 73% of cobalt assay that wasn't accounted for, and we had to try and find where this was coming from. Now, the obvious one is pyrite, that it's hosted in solid solution within pyrite. And there's also the possibility that it's within sulfates that are water soluble and therefore not captured in this modal mineralogy. So I'm just going to quickly talk about the sulfates first. And in order to do this, very difficult to capture. So we pulled out the big guns, we went to the synchrotron. I've got a scan code down there. So if you want to know the physics behind the synchrotron, that's where you go. You don't have to be about that. But we used the XFM beamline, which essentially gave us elemental maps of cobalt distribution and other elements within samples. And then we used Zanes. So what Zanes does is it targets specific energies so that it targets cobalt. And we can identify, based on spectral signatures, if that cobalt is actually present in the sample and then what it is hosted within. And we identify that by looking at pre-edge features, white line features, and post-edge features. So you come up with some really cool maps like Olivia showed as well. This is an XFM image of this particular sample here, and it's colored by RGB. Iron is red, calcium is green, and cobalt is blue. And you can see here that you've got an iron oxide core, and then you've got growths of gypsum that sit on the outside, and then you've got these accumulations of cobalt, copper, and nickel also sitting around the rims of this iron oxide grain. So when you look more specifically at this grain, you can start to see how friable this material is. It's really fine grained and pretty difficult to characterize using macro scale characterization techniques, which is why we went to synchrotron. Then looking at the Zanes data, when you look at this strip across here, you can begin to understand the different cobalt distribution through different minerals and hosts within this particular zone. But we're really interested in this major zone of cobalt host here. And so the Zanes signature that we got was this one, which is actually a really beautiful Zanes signature. It was very exciting. And we were able to fit that against a model and against the standards that we had run, and begin to identify that, yes, this was definitely cobalt. It had the correct white line position. And then we began to look at the post-edge features and identify what the cobalt was sitting in. And so the overall conclusion was that acidic fluids have been flowing through this area, and then they've associated with the surface chemistry of the iron oxide. Cobalt has precipitated out. It has adsorbed onto silica, magnesium phyllosilicates, onto hydroxides and also sulfates, all mixed together in this mush that sits on the edge of these grains. And so the implications about this are, is this water soluble? Is it suitable for leaching, conventional leaching, bioleaching? They're all really exciting possibilities to think about. But you're going to have to read my thesis to know more about it. So the next one that I want to talk about is pyrite, because cobalt sits in pyrite at this particular site. And pyrite, when you think about recovering it, it is really flotation that we'd be looking at. And so flotation is affected very much by textural surface conditions and surface chemistry and the liberation of these particular elements. So we've got pyrite with galena, pyrite with chalcopyrite, which probably floats pretty well. Pyrite that has really porous material and fractured material, pyrite with cobaltite rims, fine-grained pyrite sitting within silicate agglomerates, and we want to know which pyrite to target. So we look at the mineral liberation of these pyrites, and you can see that about 60% of the pyrite is liberated and 40% is locked within gangue material. But when you start to look at that, the P80 of the pyrite is around 70 micron, and the P80 of the tailings is 170. So you start to think, okay, I can understand why 40% is locked up. And we might have to look at a regrind process to be able to unlock and liberate those minerals. But then you have to consider your elephant diagram and where that sits in terms of conventional flotation range. And if you overgrind, then are you then having to look at more unconventional technologies like fine particle froth flotation and things like that? So all things to consider. We also then wanted to understand, well, I wanted to draw a link between cobalt concentration and the type of pyrite grain. And so I classified, 1,200 pyrite grains according to grain size, texture, and grain margins, and used laser ablation on these samples to be able to identify cobalt concentration. And from this, we could tell that the majority of the grains were small. They were generally internally altered and had altered margins around them. When you look at cobalt distribution within these grains, over 50% of them had cobalt greater than 200 ppm, which is cool. And 20% had cobalt over 600 ppm. But in terms of the actual characteristics of that cobalt and those pyrite samples, what we found was that the majority of them were really small. They were fractured and porous, internally altered, and they had this alteration margin around them. So the implications are, we need to regrind, we need to polish the surfaces. It also has implications for the genetic history of these pyrites and how cobalt came into the system. So then using the laser ablation data, I was then able to look at cobalt deportment in terms of where it sits within these pyrites. And 85% of the pyrites actually had cobalt within solid solution in the grain. There were 12% that had it zoned in the grain and only 3% with micro-inclusions, which is pretty cool because if we're going to recover pyrite, we want the majority of it to actually have cobalt hosted throughout it. But what you can find is that the smaller the size of the cobalt zone, the higher the concentration of that cobalt. The other cool thing that we found was that there were several other elements that were enriched in these pyrites. And it makes you start to think about, if you're creating a pyrite concentrate out of this material, what downstream processes can you use to recover more value other than just cobalt out of this material? So here are the different metals that we found in our samples. And these actually all sit in the Australian Critical and Strategic Minerals list. I've got plotted here the min, max, mean, and median values and compared that to the crustal abundance. And you can see which particular metals sit much higher than crustal abundance, which is very exciting. So we would be interested in looking for cobalt, copper, silver, arsenic, bismuth, thallium, antimony, selenium, and lead in these pyrite grains as well, which is pretty cool. So from this story, I've chased cobalt and I'm now capturing it, which is pretty exciting. We did the tailings characterization, then moved down into the facies, looked at the different zones of enrichment, the mineralogy, what the cobalt hosts are, the particle characteristics of these, and then how cobalt actually deports within these particular particles themselves. And this is all a comprehensive geometallurgical characterization approach, which is super important if we're looking towards a zero waste future for our mining industry. It helps us assess the valorization potential. We can start to discuss the recovery of a saleable product. And we can also look in terms of an environmental footprint reduction from the desulfurization of these materials. So I just wanted to say thank you very much to my supervisors, to Anita Parbhakar-Fox, to Rick Valenta, and to Elaine Whiteman. Also, thank you to the GSQ for their funding and to everybody who has contributed to this project. If you want to know more, my 80,000 word thesis is going to be due in September, so you are more than welcome to read it. And thank you very much.
Thanks, Loren. There is a question here already that's just popped up from Hong Peng. Very interesting phenomena. Does cobalt absorption by clay minerals behave like an analog for rare earth element absorption in clay?
Ooh, that's interesting. Don't know. I will have to read more into it. Very simple answer.
It's a great answer. So again, if there are any questions for Loren or any of our presenters, you can ask them in the Q&A section, and then they can get to those while the following presentation is going. But our next presentation is Refilwe from Geochemical. And Refilwe will be talking about developing technologies for cobalt extraction from mining tailings in Queensland. Take away, please, Refilwe.
Okay. Okay. Thank you for the introduction. So, okay. So I'm going to be giving a presentation on our projects here in Geochemical. So we are very interested in recovering cobalt from waste rocks, and that is the theme of this presentation. So Geochemical is really focused on taking the steps towards diversification of cobalt supply sources, as it has already been mentioned. You know, there is a problem with supply depending on the countries, and Geochemical is very interested in that. But for this particular presentation, we here at Geochemical are very interested in developing technologies for cobalt recovery from mine tailings. And in particular, we have obtained some samples from Queensland, as Anita has already stated. For this particular presentation, even though we are interested, let me put on the laser. Even though we are interested in the whole process of processing from mineral processing to the metallurgy, I will only be focusing on the flotation part. So first, from the mineral characterization of the samples that we received. So in actual fact, we got samples from 2 mines, but from these 2 mines, there are 2 types of feeds that we obtained from this mine site. So I'll start off with mine A, where we had mine sample A, which is stored tailings, that is those that were from the tailing dams. And from this sample, we did ICP analysis, and we found that there is around 0.05% of cobalt in this sample. And while doing the MLA analysis, the characterization revealed that indeed cobalt was hosted in pyrite, as Loren has already said previously in her presentation. So this is the same mineralogy that we observed here in Geochemical. And then we did particle size distribution. Because these samples have already been processed before, we are expecting a certain size, or we already hypothesize a certain size of the particles, but we need to confirm that for us to actually carry out flotation. Are we dealing with small particles, or are we dealing with large particles? So in particular, when we look at both sample A, which is our stored tailings, and then sample B was obtained from the current slurry tailings, that is the current operations. We note that indeed the particles get finer, especially for the current samples, while also we have finer particles with the stored, but there is a range. So when we observe the pyrite minerals, or the pyrite minerals that host copper, and in this case, I'll refer to it as pyritic cobalt, because that's where we find most of our cobalt, it is highly liberated, which is a good sign for us, especially as we are going to carry out flotation. And then for this sample, we carried out some flotation. So I'll start off first with the A sample, which is the stored old tailings. And here we are very interested in the effect of xanthates, because these are quite famous for floating sulfide minerals. And we also investigate the effect of activator. And these are just the experimental procedures that we did. You can look at it later on. So from the observations or the test that we carried out with different collectors, we note that we wanted to find the best xanthate that gave the best performance for cobalt processing or for cobalt flotation. And what we observed here, out of the 4 that are stated here, almost 3 of them gave a performance of at least 54% recovery. And given this, then our deterministic selection will be based also on the grade. So from this, we did some tests where we used copper sulfate as our activator. We're using copper sulfate as the activator because the pyrite, most of the pyrite is in the tailings, and pyrite typically in a flotation plant is regarded as a gangue. So it is mostly depressed or rejected to the tailings. So we need to activate that because pyrite is already a sulfide. So there were some depressants that were used before. So from the observation where we used PEX or potassium ethyl xanthate, we found that at least about 56% recovery was obtained, but the grade quite improved to 0.508%. And when we looked at the tailings for this test, we've also found that the pyritic cobalt that was rejected had finer particles. And then we did also flotation for the current slurry tailings. And for this sample, that is sample B of mine A, the xanthates studied here exhibited varying affinities for cobalt minerals. Why? We thought maybe because these are current ongoing operations, it might be a problem of reagents that might be affecting the chemistry or the absorption of the xanthates. That being the case, we also carried out some mineralogical characterization for the samples that we got from mine B. And from mine B, what we found is that cobalt here was around 0.04, which was almost similar to sample A in mine A. And unlike the previous samples, here we had cobaltite mineral that was 100% host for the cobalt. But then when we look at the sample B from mine B, we observed a slightly higher cobalt concentration of around 0.39. And here we observed that cobalt is with cobaltite, as well as cobalt is associated with pyrite and arsenic. So that might also be important to note, the arsenic concentration. And in this particular concentrate tailings, the cobalt was mostly associated with or it was distributed mostly to the cobaltite. And about 30% was in pyrite, cobalt, arsenic. And similarly, we also observed that the minerals of interest or the cobaltite is highly liberated, which is good for our case, we think. And then when we look at the mineralogical characterization, we observe that the samples, both samples actually have finer grain particles. The pyrite cobalt, which is only in the concentrate tailings, and the cobaltite, which is mostly in the final tailings as well as the concentrate tailings. So it is interesting observation that we made for the cobaltite graph, because we think this is because of the lower concentration of cobalt in this particular sample. Hence, we are getting such graphs. And then we did flotation for this sample as well. And here we just only focused on the steering speed as well as the pulp density, utilizing the some of the optimized conditions from the mine A. And here we noted that there is a difference when we increased our speed. When we increased the speed, we had higher recoveries. But of course, with increase in speed, we saw that the grade was declining. And this would have possibly been the ability for other gangue minerals to easily float because of the rotation speed. And then we also did tests with pulp density, where we increased the amount of solids as the feed, and we noted that at 30% there was a high increase actually in our recovery of cobalt to about 70%, but quite significantly lower grade for this sample. And then we try to do a mini flow sheet for the sample. We did our rougher and then our cleaner. So our final concentrates, we had a grade of 0.5% of cobalt with 57% of cobalt recovery. And then for the sample B, which is our concentrate, and the ones that actually had a little slightly higher cobalt grade, we observe a similar trend in the effect of steering speed. A higher steering speed actually led to more of cobalt being floated at about 72%. And of course, the grade also declined. Why are we seeing these results? And we thought that at this high speeds, the attachment process becomes less selective. So that is why we have a lot of gangue coming in and attaching to the bubbles. And then we also did pulp density studies. And by adjusting this pulp densities, particles became well dispersed, thus allowing for efficient particle bubble collision and leading to that successful attachment. In this study, what we concluded is that a moderate pulp density is best, and it yielded optimal conditions for cobalt recovery. Right. Similar to what we did with sample A, for mine B, we also carried out flotation up to the cleaner stage. And here we could upgrade the cobalt to 0.70% at 71% recovery. So as I noted previously, these are samples that are fine particles. So we wanted to find a technology where we can actually attach or make it enable the finer particles to attach to the larger particles. And we did carrier flotation. Carrier flotation, we just introduced larger particles of pyrite so that the smaller particles could bind with the larger particles and actually get attached to the particles and then float. And from this test, we actually had an improvement in recovery. We had more than 70% across all the tests, across all the samples that were tested, but we noted a decline in grade. So for mine A, we had 0.12, and for mine B, sample A, we had 0.10, while for mine B, sample B, we had 0.48. This is expected because we already were expecting this because we are introducing another mineral into the system. So that was probably the cause. But recovery-wise, we're very happy with that. And then finally, we did some carrier flotation recycle test for the samples. And what we found, this is sample A from mine A, we were able to reach about 68% at 0.48% of cobalt. And then we also did the same with mine B samples. Unfortunately, for sample A, carrier flotation was ineffective, mostly because it was our target, it was way lower for our target at 60%. And then for sample B, this one was interesting because we got even a higher recovery than expected at 87%. So actually, carrier flotation in this part improved cobalt recovery. So from our studies or from our tests that we have already done so far, we note that we have validated the possibility to recover cobalt from the mine tailings and confirmed the utility of the copper tailings as resources for critical metals. It is possible to actually concentrate by flotation, but it is now important to optimize the flotation conditions. But, you know, looking at samples such as cobalt, where it doesn't occur in a lot of deposits, most of its deposits are copper deposit or nickel deposit. So there are going to be some challenges. And one of the challenges that we noted in particular for this is the presence of the pyrite, or actually the occurrence of cobalt in pyrite, how are we going to deal with it in later processing is very important thing to consider going forward. And then we also have a problem of the fine particles of minerals of interest. And then we have a problem, or we could have an issue with the presence of past reagents that could affect the water and mineral surface, or the absorption of the reagents that we want to use now as we try to concentrate those that were rejected previously. So what is next for us here at Geochemical? We are very interested in developing further refinement processing for cobalt and for cobalt and those associated with mine tailings. So our project, as Anita had already stated, was a collaborative effort between Geochemical and Queensland GSQ, as well as the University of Queensland. And we would like to thank them for their for supplying the samples, and also the companies that are associated with the samples. Thank you very much, and thank you for your attention.
Thank you very much, Refilwe. Are there any questions that people want to ask in the Q&A just while we're looking at the transition? If anything pops up in the next couple of seconds, that'd be great. Otherwise, we can move on. And if you have a question, please put in the Q&A chat and we can answer them during the next talk. So our next presentation is from Daniel Lay from SMI, who's going to be talking about waste separation using high voltage pulses. Thanks, Daniel.
All right, is that coming through?
That's great.
All right, well, thank you everyone for sticking around. So I'm Daniel Lay, I'm a postdoc here at SMI, and today I'll be talking about waste separation using high voltage pulses. So a bit of an overview for the presentation. Today I'll give some context. I realized high voltage pulse is a bit of a niche area, so I'll give a bit of a background and overview of that. The mine samples that we did our test work on, what we actually did in our experiments, the results we have so far, and then at the end just give you a bit of a taste for some of the other high voltage pulse work happening at UQ at the moment. So for the context of this, at SMI, we've got the MIWATCH team, which we've heard from a lot today, working on characterizing mine waste. There's also the team I'm involved in, the separation team, who investigate different separation technologies. So the idea was to have these two teams work together. So use novel separation technology to extract value from mine waste. And the novel separation technology we'll be talking about today is high voltage pulse breakage. And what we'll be extracting that value for is the metals to metals project with Anita. So looking at getting the metals for the upcoming Brisbane Olympics and sourcing those from mine waste. So in terms of high voltage pulse background, if you have some simple, just get the laser out, simple electrical circuit like this, you have some energy storage device, in this case a capacitor, that gets charged up. Once this closing switch is closed, you then have a very high voltage at the top electrode, zero or grounded voltage at the bottom. That voltage difference creates an electric field, a very strong electric field. And if that is above some threshold value, you then get electrical breakdown taking place. So lightning forming, and that's what we use to break our rocks apart. So one thing to note is the process does take place in water. So in terms of what's physically happening in the rock, this is a nice set of diagrams found from a group of French researchers. So you have your electrode at the high voltage electrode at the top, your ground electrode at the bottom. And with that very strong electric field you have between the electrodes, you then get polarization and charge separation occurring along grain boundaries. That then represents a point of electric field concentration, which is attractive for that discharge to develop along. So you then get your discharge going through those regions of strong electric field. Once you have a direct connection between the top electrode and that ground electrode, you have this massive increase in heat and conductivity, and that splits and breaks the rock apart from within with these shock waves and tensile fracture. And you break your rock that way. So one of the first areas or advantages of high voltage pulse breakage that got our interest here at UQ was the idea of pre-weakening. So if you can imagine this sort of network of cracks and fractures throughout the rock, even if it doesn't physically break the rock, you'll still have all those cracks left behind. So you can often even just physically break these rocks apart using your hands, which is what I did in this photo shown here. So if you then have subsequent comminution steps, you can make significant energy savings in that because the rocks are already pre-weakened. But what has driven a lot more of our recent interest in this technology has been how selective these high voltage pulses are. So if you have a high grade particle sitting next to a barren or low grade one, that high grade one is much more likely to be selectively targeted and broken by that lightning discharge. So very selective between particles. And also within a particle, as we saw with that diagram from earlier with like the charge concentration building up along grain boundaries, you also do get breakage and crack growth occurring along those grain boundaries. So this is an example of a gold copper ore where it didn't appear to be much mineralization along the surface, but it was pre-weakened, broke that apart with my hands, and then you see this nice bit of mineralization inside the rock that has been nicely exposed by the high voltage pulse discharge. So one of the ways that we can take advantage of this is with pre-concentration. So if you have these, a high grade rock and a low grade rock sitting next to each other, the high grade one is much more likely to be selectively targeted. It also breaks much more effectively. The low grade or the barren particle, it's much less likely to be hit, but even if it is just by chance, it won't break as effectively. So you have this distinct difference in product sizes between particles that are high grade and which break really well, particles which are low grade, which don't break very well. So you can then separate out a high grade stream of broken products and a low grade stream of the unbroken or minimally damaged products. So you can then focus all of your further processing efforts and energy on that high grade stream and make your energy savings that way. So, not advocating that high voltage pulses replace traditional comminution devices, is just to serve as a supplement. And you really only want to be putting in as much energy as you have to, because once you start getting down into really fine breakage, it just uses way too much energy. So as coarse as you can get away with. So the mine waste samples that we did the test work on was Belgammon, which Olivia spoke a bit about earlier. So an abandoned copper, silver and tin mine, and Richton, which is an abandoned gold mine. And both of these were waste rock samples. And the big question was, well, can we do this pre-concentration approach with these samples from Belgammon and Richton? So potentially an ore sorting or scavenging application. The experiments, so we processed these samples using a Sulfurag lab unit, which is a commercial off-the-shelf high voltage pulse unit that we have here at UQ. So how this works is behind this red panel here, you've got your stationary high voltage electrode. You then have a processing vessel, which fits into this bit here. There's then an internal lifting table, which then lifts the processing vessel up towards the stationary electrode. So this is a simplified diagram of what that processing zone would look like. So this can only process a handful of particles at a time. So if you have a lot of sample to get through, that would just mean doing a lot of batch tests. So we used a 37.5 to 26.5 millimeter sample, looking to get about 6 to 7 kilos, and that feed was then processed until about 80% of it was passing a 22.4 millimeter screen. So we'd grab a handful of sample, put that in the processing zone, apply our discharges to the sample, tip that processing vessel out onto a screen. Any of the undersize would be stored in one location, the oversize separately, work through all of the feed. That would then constitute one cycle. The oversize from that first cycle would then be fed back in and would repeat the process, and that would be cycle 2. And we just keep repeating that process until we'd hit that target of 80% of the feed being less than the screen size. In terms of the actual equipment settings, so 185 kilovolts, so quite a high voltage. The electrode gap that we used was 40 millimeters, and we're applying 2 discharges per batch, so 1 discharge per second. In terms of the results so far, so we also did some assays of the as received samples, so you can just get a feel for what we were working with there. After the high voltage pulse treatment, these were the particle size distributions. So, you know, the same cutoff criteria of 80% passing that screen size, but the Rechtin sample was much finer and used less energy to get there. So only needed to do 3 cycles to reach that target with Rechtin, whereas we needed 9 cycles with Belgamin to get there. So the size reduction isn't the main reason why we're interested in HVP technology. It's the selectivity and their pre-concentration. Unfortunately for the pre-concentration, we're still waiting on assay results, so can't sort of share the main results for this work just yet. And I think those will really inform what sort of further tests we do. If things go really well or really poorly, we could then, for example, dive into the mineralogy and see, well, what's the reason behind that? But just as an example of what we would be doing, so you'd size the products, get the masses in the different size fractions, assay those different size fractions, then calculate a cumulative mass and a cumulative metal recovery. So this is an example of a sort of pre-concentration curve we'd generate from a different project. So this was a gold copper ore looking at the pre-concentration of the copper. So if you were to look at if your results were to fall along this y equals x line, that would mean you're not getting any selectivity and no pre-concentration. So 50% of the mass being recovered in 50%, or sorry, 50% of the copper being recovered in 50% of the mass. And falling along this line is typically what you'd see with mechanical breakage. Whereas with this sample, we did get pre-concentration occurring. So you could recover 90% of the copper in 70% of the mass. So you could reject 30% of the mass and still have 90% of your copper. So that's the sort of thing we'd be doing for this project, looking at the copper, the silver, tin, indium and gold recoveries and seeing what sort of pre-concentration curves we get from those. In terms of the other high voltage pulse work that's happening at UQ, so we're really trying to pushing getting this technology commercialized. So trying to move from this sort of small scale batch process stuff like the self-rag unit to something that can actually be used on an industrial scale. So I've got a few research initiatives. We've got a Trailblazer project working with Newmont and Sedgman. We've also got a collaborative research program with a few different industrial partners. So Newmont, Rio, BHP, Huazhong University of Science and Technology in China, who are generator and electrical systems experts, the UQ Complex Ore Bodies program, as well as the ARC Center of Excellence. And in terms of the equipment that we've got, so there's the self-rag lab unit, which I've spoken about today. We've also got the flexible testing facility. So this high voltage pulse generator is a custom built one by our partner university at Huazhong. So this, whereas with self-rag, everything is fixed and it's a bit of a black box as to what's actually happening inside. With this one, we know every detail. We can customize this and modify it any way that we want. So one example is a new set of electrodes, which we're trialing out called the Grizzly electrodes. So whereas with what I've spoken about today, you'd have the high voltage pulse breakage in one step and then size-based separation and screening in the second step. The Grizzly electrodes combine this into one step. So as soon as those particles are broken, they fall through the electrodes, So you then have your broken high grade undersize, whereas your oversize moves off to the end. So if you don't apply any more energy than you absolutely have to with this electrode system. In terms of some of the challenges for the future, so in areas we're going to keep doing research in, so ore type effects is a really big one. So even just in the results today, seeing the difference in the breakage response of Rech and Belgammon, we know that things like texture play a big part in this. Heterogeneity is another big one. So you need differences between between your rocks for the lightning to sort of pick out those differences. And yeah, I think the more ore samples we can test, the better, and build up a good data bank there. So just summing up, we've processed the Belgammon and the Rech samples. We've noted some differences in breakage. Unfortunately, still waiting on the assay results, which I think is the main thing that we're going to be looking at. There's a bunch of other, I think, really exciting commercialization work happening at UQ. And yeah, we've seen a bit of the ore type effects today, and that's definitely going to be a big area of research for us in the future. So that was all for today. Thanks for listening.
Thank you very much, Daniel. So Rick's just had to step away for a minute, so I'm going to be emceeing for the next little while. So any questions for Daniel, please put them in the chat. And certainly we're very excited to collaborate with yourself, Daniel, in this space. Got lots and lots of waste rock to come and test. And I know when you say ore there, obviously you also mean waste rock or waste materials as ores as well. So just something for everyone to rethink about there. And I might just give a big shout out to Nathan Fox too at TDK, who's been helping a lot with that particular project. Thank you, Daniel. Questions in the chat, please. And without further ado, let's move on to Gavin Rech. So Gavin is based down at TOMRA, and Gavin and I have a little wager at the minute as to who is going to speak faster in their presentation. So let's see how we go this afternoon, Gavin. So over to you. Thank you very much.
Hi, thank you, Anita. My name is Gavin Rech. I work for TOMRA. Oh, I'm assuming you can see my screen. Tell me if I've done something wrong.
Yeah, it's perfect.
Okay, so I work for TOMRA. We're going to talk about sensor-based sorting, specifically on mine waste. I'll tell you a little bit about how sorters work, because I always have to do that, and then how we're going to apply it to these specific applications. Disclaimer: read it at your own convenience. People always ask me, how big is TOMRA and how often is sorting used and stuff like that. And it's 20 years ago when I started, it was a very small thing, a very niche, but now, we're a 2 billion Australian dollar company. If you put your bottle in the wall, it gives you 10 cents. TOMRA makes all that stuff. We do all that. We do all the recycling. We do the food. We do the mining. We sort particles. That's what we do. So we're a huge company globally across, various different countries. They always ask me, where is it being used in terms of mining? And that's the graph there. This is the distribution of sorters that are being currently run, not just installed, but currently used globally. You can see we have a lot around Australia. We have about 25, 30 running in Australia. And we have the second biggest sorting plant in the world going in the next couple of months in West Australia. Obviously, Southern Africa and North America on the diamond mines up in Canada in that area. Industrial minerals in Europe. Phosphate in Saudi Arabia is a huge one. Quite a lot of minerals across South America. But interestingly, if you look at what is used in terms of sensors inside sorters, by this graph here, XRT, X-ray transmission, these dark blue sections here is king. We use that predominantly across all sectors. X-ray transmission is like a baggage scanner. I'll show you how that works. And then we have laser and color systems are the next two up there, and that solves about 70–80% of our problems in terms of sorting. That's what we'll use. In terms of mechanical platforms, most sorters are either chute sorters or belt sorters, which is exactly what it says on the can. So we have a variety of chute sorters. So chute sorters, rocks fall under gravity down a chute, and we scan them and eject them. We have a big one for primary rocks, secondary rocks, tertiary rocks, roughly after the tertiary crusher. So we are dealing with rocks here. We are dealing with millimeter scale stuff. 2 millimeters is a bit small unless you're in diamonds or salt or something weird like that. So pretty much in our world, in the waste dump world, you'd be plus 6 millimeters at least. So one of the questions when you're looking at a rock dump is how much of it sits under 6. And if it's tailings and fines, then most of it sits under 6, and you can't sort it. You can't sort particles smaller than 6. It's a particle separator. It doesn't take fluids, it doesn't take dust, it doesn't take slurry. So if you're looking at plus 6 millimeter material, you can have the chute system, or you can have a belt system. And most of our competitors and most people around the world will make one or both of these platforms in some variation. Then you can pick whichever sensor you want to put inside that machine. In general, we have our optical systems, our surface measurements, the stuff that is looking at the surface of the rock, like you have a laser scanner or a color system or a near-infrared scanner. We have those operating in the chute machines, and I'll show you how that works a bit later. And then we have our penetration technologies like the X-ray transmission going straight through the rock, and the electromagnetic stuff, just detecting the conductivity, magnetic susceptibility of the material. Those work on belt machines. So, but, that's our sensors that we use in our machines. Mostly we have all sorts of weird and exciting sensors. We have a lib system, we have a terahertz system, we have an XRF system. We've looked into microwaves and all sorts of crazy, wonderful ideas. So we make all of it. We just use the ones that are practical. We're very much focused on putting stuff on mines and actually utilizing it. This is a video, so let's see how it goes. Even if it's a bit stuttery, we should be able to talk you through it. So there's links to all of this on our website as well if you want to explain to people how sorters work. That's the core machine we make. It's about 12 or 13 meters long. We make a variety of machines, but this one is about that length. It weighs about 12 tons, this machine. And what it does is it takes pre-screened rocks. So let's say we're doing that 6 to 18 millimeters or 20 to 60 millimeter pre-sized rocks, distributes them across the belt traveling at 3 meters a second, accelerates those particles, separates them out from each other, presents them to the X-ray system, which shines down through the rocks, through that blue line, which is not really there, but through the line onto the sensor below the belt. And that X-ray transmission system then provides us a raw X-ray image of that rock. So you get a raw X-ray image like you would of your arm if you went to the doctor, or a baggage scanner if you're at the airport. And then we classify that as high density or low density atomically. So base metal sulfides or whatever we're looking for. Then by the time it gets to the end of the belt, we have somewhere between 150 and 250 air ejectors. They will open up and move individual rocks over a splitter plate to create the two separated streams. And that's how we sort rocks. That's how we take one stream into two streams. Sounds a bit like Star Wars, but they run at 10,000 particles a second. And we have some mines that have been running them for 20, 25 years. So they really are they are a piece of the landscape. If you look a bit closer at how the X-ray system works, that sensor generates that raw X-ray image that we saw earlier. And if you look at the inclusions inside this rock here, and I'll show you even better pictures in a few slides' time, you can start to understand the resolution of the sensing system that we can produce these days. We have a 0.8 by 0.8 and even a 0.4 by 0.4 millimeter pixel. So we can detect, tungsten down to a few hundred microns, or gold down to a few hundred microns, or lead is easy to detect. So we can see very, very small inclusions. It gets more difficult when you low density material, if it's oxidized, if it's a bit smeared around. But if you have a very localized inclusion, we can see them at the micron level. And then basically you tell the machine how many inclusions you want. Do you want 40% of the rock to be a high density metal response? Or do you need anything more than 5% of the rock to be a high density metal response? And you can change that while the machine's running. And then it separates those particles out for you automatically. Where do we use sorting? Well, today we're going to talk about waste rock dumps, but you can use sorting anywhere where the particles are bigger than 6 moles and you have some sort of physical liberation. Obviously, if all the rocks are the same grade and if all the rocks are the same, I can't move any rock from each other, right? You need liberation for beneficiation. And so I'm sorry, Kadia, but I can't help you because all your rocks are the same grade. That sort of porphyry stuff where you don't have the liberation is quite difficult, but most rocks have some level of liberation and we can sort them in some size range. How do you determine whether rocks can be sorted? So we work with Anita and Nathan and all the guys at SMI and the people there to evaluate different ore bodies. And what we'll do is just take rocks, throw them through the actual machines. We don't do laboratory level stuff. We just use huge machines. And we take a picture of those rocks and we determine whether we can see inside them and what we can see them. But then we separate them from each other and we return them to an assay lab and they get assayed and we see what we've got. We normally have a very good idea of what we're going to do, but the assay lab then confirms what level of upgrade and separation and recovery we've been able to achieve. We have labs in Sydney here in Australia. We have the big lab in Germany. We have test labs in Canada and South Africa, one in Groningen, Brazil right now. So you basically throw your rocks through, and once you're excited about that, you bring us 20 tons of material, and we run the 20 tons at capacity, and we show what the sorter will really do. So it's very much a not academic kind of approach, really. It's very pragmatic. You know, if you want to go down the academic road, we can open up the R&D cupboard and we can look into crazy ideas. But the real value is in the machines that already exist and run on the mine. Once we've done these test programs, we run a nice report that says, you know, this is the raw image and this is the classified image. And these dark blue, black spots are this kind of metal. And this is what the recovery and mass pools we've got using the sorter. So we did some scans for the Strategic Mineral Institute on Richton and Balgammon. And Richton pops, it looks really nice. You can see the raw X-ray image here on the left-hand side. You can see the base background host rock there, and you can see these very high density localized inclusions. You can see individual pixels there with individual grains inside them, and you can see big blobs. And then our job is to then classify these blobs, which in this case is not very difficult, into high density or metal response, right? Black and blue stuff. And then we just tell the machine to take out anything that has metal in it. You know, in this case, that metal is galena, which is why it sticks out so beautifully, because it's lead, it's incredibly high atomic density. And it really does stop those X-rays, which is why it's black, right? So we can easily remove the galena from this particular sample. We also had quite large, massive pyrite in the sample, and it appeared in a very similar way. So we can pop that out, and essentially you give us this material. We eject usually quite a small fraction, you know, a lot less than 50%. And we can then concentrate the sulfides and the associated gold that is probably living with those sulfides into a concentrate. And more importantly, we can leave that waste as completely non-acid forming barren waste. Because we're dealing with, you know, 6, 10, 20, 60 millimeter rocks here, and we're taking sulfur grades down way low, like to where they should be non-acid forming classification. Right? Yeah, in this situation, Richton was running tens of ppm of gold, and we haven't confirmed it yet, but I suspect very strongly that that gold is associated with the pyrite and the galena. So by taking that out, we take out the gold and make an economic concentrate. Come on, there we go. Balgammon is a bit more tricky. Balgammon, we use a different process called a dual energy response to measure the overall density of the particles. And we did see that some of the particles were much higher physical density compared to the others. We can't really see a localized grain or a very high density inclusion inside these, but we are seeing that this entire rock is much higher density than its neighbor. So those blue rocks there would be a very high density rock, and I'm talking electron density, so they have some sort of most likely metal in them, right? I mean, they could be very high calcium, but I seriously doubt it. And then the red rocks are your silica alumina kind of background mineralogy. And we sorted this stuff out, and basically the blue rocks are some sort of oxidized base metal, mostly iron in this case. And it's kind of ropey. I mean, a dump's a big thing, and you can go get samples from a different part of the dump where they aren't as oxidized and they'll really pop, and we can take that sulfide out. But when you have that level of oxidization, you probably don't have the gold living with it, and you probably don't have the acid forming issues in this particular sample. So we can take that oxide out, but it's not really going to help you, right? But we can just run this material and concentrate oxide as well as any partially oxidized or sulfidic material that's still there. So it's reasonably cut and dry for, if I go back to Richton, that's very obvious. That's clear as day, very obvious way to move forward there. With Balgammon, it might be a bit more challenging, but you know, there is quite a zoo of mineralogies that live in these areas, and we have to kind of understand that in the broader context before we dismiss any of the applications, especially with the rock dumps. And then once we've figured out what we want to do and where we can do it, we can set up a little plant. Like we said earlier, we have 230 odd machines running globally. So we have a variety of little plants that can be anything from one sorter up to, I think the biggest one in the world is about 14 sorters at the moment. And this is a little plant that this one runs in New Caledonia. And it's got a big hopper, and you feed the material into the hopper, and you have a simple screen to give your size fractions. And this one's missing the second sorter, but you'll have a coarse material and finer material going into 2 different size fractions for 2 different sorters. X-ray sorters sitting under a roof, fines coming out the side, and the ejected product and the non-ejected waste coming out the end. So this would be your non-acid forming waste, and this would be your hopefully commercially viable product that you could send for toll treating or, dispose in a different way or whatever you want to do. So yeah, it's pretty simple, and it's readily available. It's pretty simple to explain. I mean, the way the machine works inside is really cool, but it's really simple to apply, to these sort of situations. The most difficult thing with dump reclamation is finding the right dump. Finding the one that's not full of clay, that's not full of trees, that doesn't have 98% of the material sitting under 6 mils. We're talking about looking for those rock dumps, not looking for the tailings dams and that sort of stuff, and trying to understand where we can apply it and how much of an economic benefit it is to that particular application, right? Which is, what we do here in Sydney. And that, at a very high speed, is me.
Thank you so much. I thought that was a really great presentation, Gavin. So thanks for that. And certainly, thinking about the vision of the future, like we've characterized these rocks, we understand what's there. And Olivia sort of gave a very nice deep dive in terms of the characteristics of the Balgam and waste rock. But it's great that we have those characteristics, but how do we relate that to the technologies that actually help us unlock, do that pre-sorting on site? I think we're certainly moving in the right direction there. And I know that certainly the MIWATCH team, we have lots and lots of barrels of rocks that we're keen to send you for more testing. Let's see if we can find some more gold. I'm not sure if you'll send them back to me after we've discovered these gold nuggets, but let's see. But yeah, if you've got any questions about the technology, or if you have an interest in sort of arranging for some trials or so forth, please contact Gavin. He'll be hanging on for the rest of the afternoon too, so just pop your messages in the chat. So thanks very much, Gavin. Appreciate that. So next up we have well, no, we don't have Gavin, we just had Gavin. We have James Vaughan and Hong Peng, who are our colleagues at the School of Chemistry. So they're just on a slightly different campus to us here at Indooroopilly. They're over at Long Pocket. And I have to say, I've really enjoyed the visits over to Long Pocket because all of the labs always so busy. There's so much activity going on in those labs where they're investigating lots and lots of new technologies in the hydrometallurgy space in particular, which they're going to talk about today. So over to you, Hong.
Hi everyone. Thank you, Anita's invitation for me and James to give this presentation. So for this presentation, I will give the introduction for our School of Chemical Engineering and the research group, and also cover some research highlights like bauxite residue. Anita already mentioned that during her presentation, bauxite residue, except for rehabilitation, actually is also great secondary resource for recovery. And we also cover the zeolite synthesis, and also from the tailings, it's called from the leached spodumene tailings. Then James will cover the research project about that rare earth elements extraction from marine uranium process tailings, and follow on some summary and outlook. First things, UQ, I always put these special jacaranda flowers as a representative for UQ campus, and also for every undergraduates for their end of term examination date. Make sure they are passing by without dropping any jacaranda flowers during the November. And on the red part is our new Andrew Leveris building, is for the home of the School of Chemical Engineering. We have these fancy facilities, and you guys also welcome to visit our new buildings. Just a quick update about metallurgy major in the School of Chemical Engineering. Actually, we cover the 3 major classes: pyrometallurgy, hydrometallurgy, and mineral processing. It's in total as a metallurgy program. And currently the program leader is James Vaughan, Associate Professor James Vaughan, to cover that. And how we also appreciate that the SMI also providing help on that course, process mineralogy and combination, and other courses covered by the staff from the School of Chemical Engineering. And for our hydrometallurgy group, I just have a quick introduction for the counter projects. We have this sustainable process of a rare earth. I think that's is collaboration with Anita. And we do also have other project like pressure oxidation with the refractory gold wars, previous with Newmont. And we also have gold leaching fundamentals linkage with BHP Newmont. And we have a project with Rio Tinto on Sandy DSP process that's related with bauxite aluminum process. And the last project is also about the metal depth zeolite catalyst synthesis from clay minerals and spodumene tailings for carbon dioxide utilization, and also the transformation like hydrogenation to produce like organic chemicals like methane or methanol things. So this is funded by Zeotech and also the training center. Okay, this 2 slides, I think I think Anita already covered that about the critical minerals distribution. I think here I might make sure everyone can saw this. I wouldn't go to the detail things, just to cover that as a listed that 24 critical minerals was first identified that for the Australian government. And most of them actually, even they have the resource, but unfortunately is also occupy a very small portion in comparison the world. And also critical minerals play the very major roles in the Australia economics, and it's $3.9 billion on mineral explorations in 2021 and the 2022 financial year. The next slides also it's, I think Anita already to cover for the mining waste. So here I would like to just emphasize 2 types of mining tailings. One is bauxite residue, also known as red mud. And actually, except for its alkalinity for environment dispose, you need special care for, and we call rehabilitation. I think in SMI, you guys have a big group from Professor Longbing Huang working on the rehabilitation part. But from the hydrometallurgy group, from our group, actually they are also can be a very good secondary source for like hematite, rare earth elements, and especially on scandium and the other elements for recovery. And we also cover the especially mentioned that for now the lithium boom for Australia, especially for the WA, Western Australia, they have a lot of lithium spodumene and to produce lithium carbonate or lithium hydroxide for the lithium industry, but they actually left off the huge of the tailings. Just to give you one idea, so it means 1 ton of the lithium hydroxide be produced, you will produce 8 tons of the tailings based on the simply by the chemistry and the mineralogy calculation. So that's a huge potential tailings, and with increasing the production of the lithium from the spodumene feed ore. So first things, just to cover the story about the bauxite residue. So bauxite residue is just come from the bauxite alumina industry. When you use this bale process or any other process, you produce the metallurgical grade of alumina. This alumina used for smelting to produce aluminum metals. But after you're refining from the bauxite to alumina, you actually produce the significant amount of the tailings. This is for bauxite residue or red mud. And give you an idea, it means 1 ton of the alumina produced, and you also produce a 2.5 ton of the bauxite residue. So that's give you an idea of the bauxite residue things is actually globally, you have 150 million tons being produced. And currently they have a storage about 4 billion tons in worldwide. For this bauxite residue methodologies in our group, I just gave a quick background on this research background. Is since 2014, we work with Rio Tinto Alcan based on the UQ Rio Tinto Bauxite Alumina Technology Center. We have developed various different technology, how to utilize bauxite residue, also how to utilize the low-grade bauxite to improve the efficiency to recovery alumina and also reduce the cost of the chemical reagents, mainly on the sodium hydroxide. And so that's why we have identified some very interesting findings for bauxite residue reutilization. Recently, we just identified the process is called dilute acid wash. And by the training of this bauxite residue, actually we can turn them to be very interesting adsorbents. So here is what we have published recently about that manipulating the morphology and the mineralogy of the bauxite residue. We can change that the adsorption performance to recovery the heavy metals in the wastewater from, for example, like mining wastewater, like containing the copper and lead and even the phosphate. And we identified that the totally different efficiency for this bauxite residue. And the next one is we have research about this bauxite residue leaching, as we will said that the total elements, they actually also is a potential rare earth elements, special for scandium, lithium, cerium, and also have yttrium. And we actually identify the key things is similar like you guys doing geochemistry. We actually identify the extractive association index between the major elements. The major elements you find that for bauxite residue is for sodium, calcium, aluminum, iron, silicate, and titanium. And how these major elements associate with the rare earth and like scandium things phase, and we by change the different conditions like temperature and acid concentration, we do identify that which kind of the rare earth is associated with which type of the major elements. For example, on here, you can show the data about that the scandium actually is mainly is associated with titanium and iron phases. But you will find that for lathresium is mainly associated with the silica and aluminum and calcium phases. And actually this is 4 elements is mainly associated with another mineral phase is produced for DSP, or you can call the sodalite. But for the titanium and iron phases is mainly associated with hematite or anatises phase. So this is quite interesting findings because we now identify the elements correlation between them. We actually developed the quite very interesting procedure. It's called residue to product. It's a no-cost bauxite residue utilization method. By simply processing diluted acid, actually we can produce a different product, especially for that high silica bauxite. You can look at the original bauxite residue. You have a very high sodium content and a reasonable amount of iron oxide and also titanium. By our processing, we actually produce the acid wash residue. First things, we desilicated the sodium down to sodium content down to under 0.3%. But we also enriched the iron and titanium stuff things from 37.4 increased to 85%. And the titanium also enriched to 2-fold. So this is things, actually this solid residue is also, we got our scandium stuff things also enriched and gave the significant amount of the extraction performance. Over 80% of the scandium can be recovered. Comparison original if you treat it with original feed. So this is a process we just published last month, and this is a process is very interesting to develop that. We also have done the fully technical economic analysis for this process. So this is about the bauxite residue. So now I have a quick update on the second part about zeolites. So zeolites is a very good absorbent materials. Usually currently is synthesis use pure chemicals like silicate and sodium hydroxide aluminate. But what we come out is means from the mining tailings, especially for the clay minerals or red mud, fly ash, even what we mentioned today, especially for lithium spodumene tailings. From this phase, we develop a very special patent, actually can produce impurity-free commercial grade zeolite A and 4A and 5A to using for these two major applications like carbon capture and wastewater treatment. And we were also expanding the process from the lab scale. We started from like 100 to 200 mil and end up with this processing to scale up to 2 years processing, and so finish it with the Zeotech company things. And we use, once we got the commercial zeolites product, we also collaboration with this training center and to look at that zeolite based metal doped zeolites, and we got very good carbon dioxide transformation, for example, to produce a methane. And this is very efficiency and comparison with the commercial grade and also our Zeotech products. To saving the time, just a quick summary about that things, about these two projects things. First things, the desiccated bauxite residue can be upgraded to high grade, and the scandium covalent also can be reached to threefold with a high recovery of 80%. And the niche spodumene tailings also can be used to produce high quality zeolite. And also these zeolites can be used for the carbon dioxide methylation with high efficiency. So to save your time, now I'm passing the second part of the result part, I leave to James.
Yeah, okay. Hi, Hong, do you want to just expand that? So
yeah.
Hi, I'll just give a quick update about the rare earth project. So this project was supported by the Queensland State Government Department of Resources, and as part of the project, we looked at what a reprocessing option for the Mary Kathleen uranium process tailings. So these tailings are kind of managed at the moment by the state government, and there's 5.5 million tons, and inside those tailings, there's about 16,000 kilotons of neodymium, which is a key ingredient for magnets. Sorry, not batteries, magnets that go into motors, which are used more in electric vehicles these days, and also in generators that are inside wind turbines, for example. So the grade of this kind of resource of rare earths is fairly high, actually, on the order of 2 to 4%, and about 3,000 ppm neodymium and praseodymium, noting that there's 1.5% cerium and about 1% lanthanum. So there's other rare, less valuable rare earths in relatively high concentration there. Okay, next slide. Oh, thanks. So the processing of rare earths is actually fairly complex, and there are a lot of different options depending on what type of feed you have, and there's a lot of different potential feed sources. So you can have alkaline baking type processes, hydrofluoric acid leaching, or ion exchange desorption type leaching processes for Mary Kathleen tailings, which are silicate based source of rare earths. In this case, we studied some different leaching options, but settled on a conventional sulfuric acid bake leach process, and we were able to get high extractions in a reasonable acid ratios using that approach. And in purple there, the process we followed, which I'll just describe today, is once we have the rare earths in solution, we add sodium and precipitate the rare earths as a rare earth sulfate sodium double salt. And then we take that double salt and we've converted it to a mixed rare earth hydroxide using caustic conversion. That can be further refined to then separate the rare earths and get final pure rare earth products. Okay, you want to go to the next page there. So in the process is summarized here, we have the Mary Kathleen tailings feed coming in, acid bake, leach, and it's a water leach, and the leach residue is shown there. And then the rare earth double salt is precipitated as these elongated crystals. And then when we do the caustic conversion, actually those crystals remain there, maintain their shape even as in the hydroxide form. So we have a material that's, if you look at the composition analysis down there, we have neodymium is on the far right. We have 0.3% in the feed, and then we leach out 90%. So we have less than 0.1% in the leach residue. And then we have the double sulfate salts, about 2.6 weight% neodymium, and then the final mixed hydroxide is about 5.3% neodymium. And the mixed hydroxide product at the end is a fairly pure rare earth hydroxide with the major impurity remaining being calcium at about 3%. Okay, so next slide. So the process is described there on the left, and we're going to present these results formally at a conference next month in Namibia. It's a rare earth conference. But just a summary, like a sneak peek, I guess, at the results. So we did a little bit of an economic analysis based on the reagents used in this case, and we estimate that there's the operating costs around $195 per ton of Mary Kathleen tailings, and then we expect the potential revenue from the rare earth products to be on the order of $275. So with the key operating expenses considered there, we still appear to have a potential profitable operation. And you want to go to the next slide? Of course, that's a very preliminary economic analysis. And if you were to be able to achieve that amount of profit, that would be about $440 million of profit for processing that resource. Of course, there's a lot of things that weren't considered around labor, the capital cost of the plant, energy, packaging, refining, and waste treatment. There's potential upside on the price with the demand trends compared to what we assumed in the cost model. There is opportunity to further reduce the amount of reagents required in the process, and that hasn't been fully optimized. For example, we can recycle sodium hydroxide, and we can source and use sodium sulfate instead of sodium chloride, which we did in this particular study. So overall, it's still interesting and worth having a more detailed look at this opportunity. So I think that's all I've got to say. Or is there one more slide? No, that might be it anyways.
Yeah. That's it.
Yeah, okay. Thanks.
Okay.
So happy to take any questions.
Excellent. Thank you so much for that presentation as well, Hong and James. There's lots and lots of opportunities and avenues for recovering various metals from all sorts of waste materials, and indeed sort of all materials which you've showcased. And James, it's really nice to see an update on the Mary Kathleen's study and research that was ongoing for the last little while. Certainly, I think there's going to be great opportunities to see more test work and sort of, things moving towards pilot plant scale in the next little while as well. So thank you, and good luck with the presentation in Namibia. That sounds awful. Poor people who have to go there. So if you have questions, please put them in the chat. Certainly, we're probably going to get a bit squeezed for time for the final discussion session. So make sure you get your questions in early so we can get to them, because we'd obviously love to have a very productive discussion after Enrique's presentation. So thanks again, James and Hong. Enrique, if you want to start sharing your screen, that would be great. So as I said a little bit earlier, Enrique is a PhD candidate with us here in the MIWATCH team. he's, you know, obviously one PhD is not enough work for a student to do. So he's actually been working on a sister project as a research assistant, looking at, you know, the applications of hyperspectral technologies for predicting environmental indices. And, you know, as I kind of presented a little while ago, you know, in terms of the thematic areas of MIWATCH, this really is focused on initial waste reduction. You know, if we can characterize that whole ore body, we have that opportunity to significantly reduce our future waste footprints. So without further ado, lucky last, Enrique, off you go. And thank you for your contribution this afternoon.
Thank you, guys. I'm going to be brief, as Anita was saying, and I'm just going to come back. If you remember Anita's presentation, if you were here at the beginning, that this is part of, most of the presentation of the MIWATCH was focused on theme 3, but this is one of the themes, which is the first theme that Anita was mentioning. So how we can predict some geoenvironmental prospectivity beforehand and before like having this tailings deposit in our mining. In general, now we're gonna part of this team. This is part of my research, as Anita was saying, part of my doctoral research, but also where we have like a sister project with the Geochemical survey, and this is focused on using hyperspectral technologies for predicting environmental indices. The case study was focused on 4 northern Queensland ore deposits, and this has been I'm going to present the conclusions of the last year and this year that we're still working. So without further ado. And as a way of introduction, we all know that mine wastes are generated through each stage of extraction, processing, and concentration of the life of mine. Each deposit generates various mines waste according to the type of ore and the process necessary for its extraction. In general, we have 5 types of deposits, but we have more of them are focused on the first one, production, which is waste rock and tailings. Regarding mining and tailings generation, and as Loren was mentioning in her presentation, if we take copper as an example, which is the first commodity generating tailings at this moment, figures show that historically decreasing ore grades of the deposit and increased production from the 3rd and 4th industrial revolution have been derived from increased tailings and mine waste production. We all know this formula. But actually, this is not only going to happen with copper. We know also, as the former presentation were mentioning, that we have other elements and critical elements that are going to be defining for the green electric transition and the net zero carbon net zero carbon goal. So this is going to happen more and more and with more elements. From all the mineral impacts, the acid drainage or acid mine drainage and the results have been named by the United Nations as the most meaningful potential environmental damage. So the main objective of this project is to develop and apply a workflow to identify the environmental characteristics of future waste materials, focusing on acid drainage domain. This forms part of a bigger project under the new Economic Minerals Initiative of the Queensland government between the University of Queensland through the SMI and the Queensland government through the Department of Resources. But what happens with the portion of the life of mine that I showed? And there is a stage that in general we're not considering, and how it is going to be involved in the case study that I'm going to show today. We have at this stage zero, which is the exploration, and it's an important preliminary stage that is usually not considered in the life of mine. Why is this important? Because we have an incredible amount of data and knowledge of the deposit we create. And what if we use this information in general also to assess the environmental characteristics of the deposit, even recycling info from exploration stage? We know that in general exploration stage is focused on vectorizing the deposit and determining ore growth in advance, but in general we're creating huge amount of data that we can also maybe reprocess to assess how it's going to be the environmental situation in the future. Traditionally, the mining industry has been predicting acid drainage using traditional geochemistry assays and wet chemistry, but has avoided including mineralogical characteristics on this assessment. The main problem is that this approach has yet to be accurate for several issues. It was created in the 70s, as Anita also mentioned, and it was created for the coal industry. And due to the low amount of samples we are allowed to test, it lacks a high representativity. In general, as we know, this is required for the environmental permission of a mine to start processing the deposit, but we have a lot of problems that we are not assessing in this. And the requirement of the industry is like we need to generate a new process that it has to be rapid, low cost, simple, and accurate for the acid drainage prediction within this moment. And as Daniela was saying, this is also like complementing what is already functioning as an industry standard for the industry, but this is gonna lead for a new way how to environmental assess in general deposits. As I was saying as well, this is part of the theme one of what MIWATCH is already focused working right now, which is the environmental planning acid mine drainage tools using drill core datasets. How is this generating how we can assess the acid mine drainage, mining drainage? In general, is with the calculation of many indexes, as we see on the right. And in this project, we're gonna mainly focus on the calculation of the high-level geoenvironmental index. I'm gonna go through the process in general, how we calculate the index to assess this acid drainage or acid mine drainage. We obtain the geoenvironmental domain in general. We access public domain information as is showing in the slide. We have many records with a lot of information, hyperspectral information, and geochemical information that you can see in the National Virtual Core Library. We selected some drill cores from Northern Queensland. We went to the EDC, then you have like the photo on the right of, and we obtained information from them that it was done before, but we recheck the results for line scan XRF. So we have some fluorescence data of the drill cores, and we also have hyperspectral. These drill cores in general have been scanned with the high-level technology. So we also have that data. We have some mineralogical data, and we have some geochemistry data. In general, the technologies, I'm not gonna go to in detail, but the high-level technique is working in the very near infrared and the shortwave infrared, but also can work in the thermal infrared. So we have a lot of information. We can assess the presence of minerals as the carbonate groups, micas, feldspar, quartz, and sulfates. And it's the only limitation that is a line scale that only is scanning in the mirror. I know that you probably most of the people know this information. And the mineralizer, we have a line scan X-ray fluorescence. The scale is centimeter. And we can assess some presence of some elements, sulfur, iron, copper, lead, zinc, and some trace elements in general. What if we combine these two information to obtain an index, the high-level geoenvironmental indexes, to access the acid drainage? first, I'm going to show the deposits. We have information for 4 deposits in Northern Queensland. As you can see, I'm not going to go in detail for them. And I'm going to show how we calculate then the high GI score. We obtain the high logger intensity from the high logger analysis, and we multiply this number, which is showing at the same time percentage, the presence of the percentage at the mineralogical phase that is hyperspectrally active in those infrared ranges, and we multiply that by the relative reactivity and the neutralizing potential value of the mineral that we found. We do this in general for all the mineral phases that they were found with the high logger. We sum up and we obtain the high GI score. The high GI score, we can also plot it downhole for each of the drill holes for the 4 deposits that I showed before, and we're going to obtain in general an overview of how it's going to be the acid drainage production, acid drainage production, or the presence of acid neutralizing capacity by the rock. So in general, we have the score that we obtain is uniqueness, but higher the number of the high GI score, we're going to obtain lower levels of acid drainage production, and actually the rock is offering some acid neutralizing capacity, and for low levels of the score, we are going to obtain in general potential acid forming rocks. So you can see we can plot downhole the scores, and we can see how it's going to be the potential of the acid production. We have some issues regarding this calculation because the sulfide phases, they are not calculated. The results are not with high confidence from the high logger, and we have some other phases that they don't have this relative reactivity of the neutralizing potential value. So actually, we don't have information for them. Some of them, so they're added to the high GI score as 0, but some of them maybe they can act as secondary neutralizers, as we know for some micas, for example. So as I was saying, we plot the carbonate relativity intensity. We can also obtain it from the high logger. We can also plot downhole the high GI, and we can also plot handle the sulfur percentages from the mineralizer XRF. We found that in general there are some problems because, as you can see in the middle, the high GI is showing, for example, acid neutralizing capacity for some of the intervals, but also we have high presence of a sulfur, which of course is saying that we have high presence of sulfide phases or sulfate phases as well. So how we can calibrate this? We determine to add the sulfur percentage from the calibration to the high GI score, and we in general can plot the information, the potential. We can plot all this information, and we create 5 acid drainage potential rich zones, as you can see, with different characteristics. From 1, which is more acid neutralizing capacity, to the 5, which is more acid producing material. And this was developed by Laura Jackson, also in her PhD thesis at the University of Tasmania. So from all the information, what we did, we plot the intervals with a difference of in general 10 centimeters, and we obtain how it's going to be the acid production situation for this rock. I'm going to jump this, but because we did for all the drill cores that we found for each deposit, we have more information in Mount Isa and Lysing Wolfram Cap, but in general, If we plot all the information, we can see that most of the samples are in class 5 and class 1. You need to see the high density that it has class 5. So most of the rocks can be stated as acid producers. What was the next step? We checked what was the situation per meter in general of the rock, of the drill cores that they have available. And if we also remember of the publication that Anita did with Regina Baumgarten the last year in the elements, as Anita was also mentioning, what are the next steps regarding these studies? We need to complement the sulfides in general, the sulfides, sorry, percentage. So we can do, what are the next steps? We can do automated sulfide recognition using artificial intelligence and machine learning that we're actually working right now in my research with Tech and Data Rock, which is results are confidential. We also need to do mineralogical studies. We're gonna do to QAQC the hyperspectral studies. We can use the same Magwaneng and write MLA, but also we can use general XRD as we're gonna do in this analysis. In the case studies, we have geochemistry, and we need to do the acid drainage practical test to corroborate that everything is working with the industry standard calculation. As a summary, we know that the acid drainage industry standard practical testing needs to be updated to incorporate more mineralogical information. Not everything is chemistry, right? Mineralogical and geochemical data acquired for exploration stages are routinely connected through the life of mine, and they can also be used not only for geometallurgical studies and exploration, and also for geoenvironmental studies. The high GI can be used as a domain tool, but it needs to be calibrated with detailed information and from mineralogy and the classical standard acid drainage studies that we have in the industry, as I was mentioning. We also have the possibility to extract other geoenvironmental indicators. We have possibility to check how it's gonna be the potential for secondary commodities, gas composition, mineral combination, and we can create environmental geometallurgical units, the same as geometallurgical, and we can combine all these indices and create these units. And we have an incredible opportunity to early design of mine waste facilities and reuse potential of waste. I would like to thank also Anita Parbhakar-Fox and Nathan Fox, who are part of this project, and Vladimir Lisitin, Suraj Gopalakrishnan, and Frederick Van Gnielinski from the Department of Resources and all the MIWATCH team. Thank you so much.
Thank you, Enrique. So yeah, something a little bit different for the audience to finish on there. And certainly I think, you know, I said it at the beginning during my sort of talk that mineralogy really is the key to sort of really achieving net zero mine waste in terms of future wastes and indeed existing. And I think you've showed us really nicely how that technology can actually help address some of those environmental concerns and issues that we have, and better design future waste rock dumps if indeed we have to have them. So thanks, Enrique. And indeed, obviously a PhD is not enough to keep you busy. Let's just chuck in a sister project there. Why not? So big credit to you. So thank you very much. We are at the end of our formal presentation. So yeah, I'd invite all the speakers to pop your cameras back on now. I'm probably going to hand over to Rick at this point to sort of drive the Q&A session, if that's okay, Rick.
Yep, that's fine. Anita, if I got my, yep, I'm got my, just checking to make sure I wasn't muted. Well, the first thing I would say is thanks to all the speakers. I think a really interesting mix of presentations and, very, very enjoyable. So we'll maybe start by just opening the floor to questions from the audience. If you have a question in the as a webinar attendee, there's the Q&A or the chat. Please feel free to put it in. All the panelists, you're welcome to ask each other questions. I think I saw Loren had her hand up before. So why don't you go ahead, Loren, and meantime, anybody who's got questions.
Yeah, sorry, just while everyone's thinking of questions and things like that, I just wanted to revisit what Hong asked me at the end of my talk. I didn't want to elaborate then because I knew that we were time constrained and I am seriously just thinking about the options and the possibilities. But Hong's question was essentially about how, like, if the cobalt absorption onto clay minerals behaves in a similar analog to rare earth element absorption onto clays. Now, I haven't actually considered this very much because rare earth elements aren't in high concentration in the deposit that I'm looking at, and it's a PhD and I have to be quite specific about what I'm looking at. But my understanding is, like, if I'm just speculating, my understanding is that rare earth elements absorb onto clays via ion exchange and surface complexation. And if you link that back to cobalt in my deposit that I'm looking at, the cobalt is actually sitting in a magnesium silicate. And my assumption is that probably it's a cation exchange with the magnesium of the same valence as the cobalt that's occurring in that acidic environment. I'm just sort of throwing ideas out, but I know that this material is quite soluble in just water without any reagents. So it's quite easily broken down and captured. Anyway, I'm just speculating ideas, but I just wanted to revisit it when we had some time.
Good. Thanks, Loren.
Absorbent. Oh, sorry.
Go ahead, Hong.
It's close. Sorry. I think if it's just ionic absorbent clays, you simply can do like a salt wash, just like cation exchange. But if your cobalt is actually incorporated into the crystal structure, it's very hard to just salt wash or cation exchange. You need to put like strong acid or strong alkaline to leach out. So it means release that kind of the valuable metals or salts into the solution, then do sequentially do like precipitation purification steps. So that's why I just want to have a question, ask these things. It's because it looks like similar, maybe it's different, just quite curious thing. Yeah.
Well, thank you. Thank you very much for the question.
Daniel.
Yep, I had a question for Gavin. Thought it was a really interesting presentation. I was just wondering, do you have an idea of how much energy you would typically use in that ore sorting process? So like running all of the conveyor belts and the sensors and the air guns in terms of like kilowatt hours per ton or something like that. Yeah.
Yeah, it's pretty low because essentially it's a conveyor belt with an X-ray system or a sensing system on it, or even a chute machine which doesn't use any energy. And then you just pay for the compressed air, right? So if you're a diamond person and you're ejecting 0.1%, you can go to Bunnings and buy a compressor and you'll be happy, right? But if you're ejecting 50% of a very large capacity, you'd be using 150 kilowatt compressor. So it's really the compressor, the size range and the mass ejection that determines the energy pool. And we're doing a lot of work to now change the way we run our ejectors to reduce that energy. But in general, on average, for a typical ore, you'd be using somewhere between 50 and 100 kilowatts of energy for the sorter and the compressor. But I'm generalizing across all applications there. And that's per hour. And you're running somewhere between 40 and 100 tons an hour on those sorters, maybe 150 on those sort of sorters.
Cool, so thank you.
Number on it, you can put like 1 kilowatt per ton if you want to put a number on it, but it varies hugely from almost nothing to probably 3 times that much. Right.
I had a question. Oh, go ahead, Anita.
Please, you go first, Rick.
I was just going to say I had a question for James. One of the things about the Mary Kay tailings is the uranium content, and current regulations basically make it very difficult to kind of transport that material or deal with it in any great way. Is there a strong correlation with the uranium? And I know that you've got a lot of experience in removal of radionuclides. Is there any hope of doing that in the process in a way that would allow production of rare earths from Mary Kathleen, or is it something that would require a change in regulations?
Yeah, I don't actually, I'm still a bit confused about all the regulations and what exactly is allowed or not allowed. But yeah, just to note that more than 90% of the uranium was leached out in the original process. So it's not, it's fairly low level radioactivity. It's lower radioactivity for that material than the copper concentrates that are being processed at Olympic Dam. So it's so from that point of view, it's a risk that can be managed. As far as I understand that our process will reject most of the radioactive elements, and then possibly there's still a question around thorium. I think there's a little bit of thorium might get through in our rare earth concentrate at the moment. So we haven't kind of dug into that in enough detail yet, but pretty much the product that we make, yeah, should be you know, at least 80 or 90% lower radioactivity than the tailings themselves. Yeah, there are ways. There's some technologies that we've been working on if we have to deal with radioactive lead or radium itself, then we can put those onto ion exchange resins. But again, not clear if that's required or not.
Okay, thanks. Anita, you had a question.
Yeah, I mean, I guess that was one that was on my mind to unpack a little bit more. And I guess, you know, just to continue with that theme a little bit more, I mean, the MIWATCH team, we've had the opportunity to go out and sample some of the waste rock at the site as well. And certainly, you know, through the M4 mining program, we've had drones out sort of scanning the waste rock piles using hyperspectral technologies and so forth. And, you know, we do sort of detect quite a significant signature of rare earth elements in the waste rock too. So I suppose, you know, with all the different parties on the line, maybe there's an opportunity there to sort of, you know, look at, you know, how the technologies could be used to sort of address the waste rock issue that we have there. Because obviously the tailings have a slightly smaller tonnage in comparison to that waste rock. So just something for the future there. But I guess one of the questions that I had was probably more of a leading one. So obviously Daniel and Gavin and Olivia have all had a good look at Valgammon. These materials are probably going to come to your labs next, James and Hong. So I guess in terms of, you know, some of the things that you might do to extract indium from these materials, for example, like what sort of experiences do you have in those sort of critical metals associated with sphalerite? So, you know, indium, gallium, germanium, they've been hot topics, certainly nationally, and working with collaborators in the USGS, you know, there's a growing appetite for those. So what are your experiences there?
For indium, yeah, so I've got no firsthand experience with indium, but we're gonna go, we're visiting with the students in next month in Trail, British Columbia, produces indium product from zinc concentrates as well. So maybe I'll learn a thing or two. I'll ask some questions when I'm there. But I just saw the speciation that was shown on indium so there's no oxidation reduction potential reaction. So it's just a matter of getting there's the indium cations and anions if you have a lot of sulfate in there. So maybe you could think of a leaching system where you put it into an anionic form and then put it onto an anion exchange resin to selectively recover it. Maybe something to think about or try, but I'm not actually sure what the conventional approaches are, so maybe worth a little bit of a review of that as well.
Because I'm sure Olivia will be keen to catch up with you to sort of compare notes and see how that can move forward for the next step. So yeah, anticipate those and the Richton samples. So again, looking forward to seeing some gold concentrates being made there. A bit more conventional.
Olivia.
Hi, everyone. I have a question for Daniel. It was amazing techniques. I'm so surprised with all the progress. But when you say that the opportunity to commercialize, have you know what could be the next step in terms of escalate? If it's really happened, that could be possible to include in a workflow in a mine. What could be the starting point? That I'm so curious about that.
Yeah, so I think that's then the next step would be building a pilot plant, basically. So or a pilot scale unit, and then putting that onto a mine site. So that's part of the work that we're doing in the Trailblazer and also the HVP collaborative. So yeah.
Yep. Good. All right. Well, I mean, I think we're coming up to full time, but what I was thinking, with no previous notice, I think I might hand over to you, Anita, to sum up the afternoon. I think there's a lot of the talks and a lot of, you know, the effort into putting all this together was, you know, centered around the effort of your team and its collaborators. So I might hand over to you to sum up, but I'd also just like to thank everyone who gave a talk. I think, like I said, really interesting set of talks. Good afternoon, and over to you, Anita.
Yeah, so thanks, Rick. Yeah, I mean, I was thrilled to have the opportunity to create this afternoon because I wanted to sort of step beyond the stream ones. I mean, everyone's quite familiar with, you know, all the plots that I show of, you know, where the blobs are of critical metals in our waste across the country. That's really important. But, you know, thinking about the detailed characterization that Loren and Olivia showed really sort of sells the message, and it's not selling it for, you know, the purpose of selling it. It's the fundamental key to actually unlocking the opportunity that mine waste presents is the mineralogy, and using those tools, understanding where all that value is actually hosted mineralogically, to then be able to start to design which metallurgical processing techniques best suit the recovery. So I think both Loren and Olivia really demonstrated how a multi-scale approach in terms of characterization is absolutely necessary to do that. And certainly they've done a lot more work that they couldn't share with you this afternoon, but sort of taking those next steps into sort of the flotation, how these data actually inform that is, you know, also critical. But we were, you know, very much given the opportunity to sort of explore that and have that explained to us through the presentation from Rech there at Geochemical. So certainly the, you know, exploring, you know, a couple of the ore types that we've worked on, and I'm calling waste and ore here, a couple of the ore types that we worked on, looking at the opportunity of how we can actually recover and concentrate, you know, pyrite into, you know, a con that can be processed was really good to see. And not just from the existing tailings, but from the operational tailings too. So I think, you know, it's important to understand that ore bodies are heterogeneous, and that doesn't stop when we're dealing with waste environments. So what might work for one particular area of a waste repository is not necessarily the same as what's going to work for another area of that. And certainly capturing that heterogeneity, as Loren showed, is absolutely vital to feed into the next parts of the problem. So we really do have to think of these as complex ore bodies. So that was great to see as well, and I'm excited to see where the next steps go. And certainly, you know, the carrier flotation technology is something that I believe is undergoing patenting. So I think that's a great outcome for the work that was done there in collaboration with UQ and the Queensland government. But moving forward, you know, the opportunity to work with new technologies to actually do that boots on ground, you know, sorting that we saw from Gavin, absolutely fundamental. Like, I mean, we've been saying for a long time, we need modular technologies. We need to take the technology to the field, because we can't necessarily expect a pilot plant to be retrofitted or sort of, you know, new pieces of infrastructure to go on. But if we have, you know, smart METS companies like TOMRA that can actually deliver solutions that mean we can take that technology to site, we can reprocess that waste rock dump. I mean, the dump that Olivia showed us there, polysulfidic, impacts on the Jamie Creek. It needs to be managed in terms of, you know, breaking the source pathway receptor through that reprocessing. You know, that pre-concentration, you know, in terms of making all those sulfides concentrate in one area and doing that environmental de-risking that we could achieve with TOMRA's technology, I think is, you know, transformational for lots and lots of AMD sites. So, you know, really excited to see where the next sort of steps go with the TOMRA technology. But again, you know, as Olivia said, very exciting to see the work from HVP. I mean, once we've got, you know, these cons, we might need to sort of further, you know, separate and refine them. We could do that using HVP, as Daniel showed very, very elegantly there. And those assay results are absolutely pending. We're really sad we couldn't get them to you today. But, you know, you're all going to have to stay tuned to see what the next piece of the puzzle is. And I think it's going to be quite positive. Let me put it that way. But certainly, you know, HVP is just going to be another transformational technology, both in terms of that pre-concentration and that environmental de-risking from the outset and redesigning flow sheets like that, but also it has that application for its waste rock materials too. You know, Hong and James have given us an insight into the complexities of hydrometallurgy. You know, it's not just, leaching is not just some simple thing that just happens at the end. It's so complex, it's so dynamic, like the separation of metals in solution, you know, so many factors control that, pH, EC, you know, lots and lots of different things. And, you know, the team busy working away, you know, taking the information from, you know, the characterization work right through and using that to inform what they're doing is great. And there's so many new technologies coming out, and certainly I'll show that one of my slides. You know, we haven't yet scratched the surface in terms of all the tests, what we could do. And, you know, there's just going to be so much more to do and so much more to commercialize, which is great. So last but not least, Enrique, you know, this is one of my pet projects in terms of, you know, my own core interest from my PhD days. But certainly, you know, if we're going to really seriously reduce our waste footprints, we have to think smarter. We have to do better flow sheet design. And certainly Enrique has given us a really good example of how we can use all of that data that we have at our fingertips, you know, kilometers of drill core data. How can we optimize it better to, you know, mitigate against AMD, acid mine drainage, or indeed, you know, find additional commodities in there. So, you know, the power's there. We just need smart people like Enrique to sort of pull through that data and develop these indices that help us domain at that outset, how we can sort of look for new opportunities for product design, byproduct design, and indeed sort of manage AMD better. So I think overall it's been a very big afternoon. I think there's been so many awesome, you know, presentations. We could go on for hours more, but I think everyone probably needs to get home, myself included. But please reach out to ourselves. You saw, you know, the diversity in the MIWATCH team. There's a lot more work that we've done. I was expecting people to ask me to put up more maps now, you know, where's the gold, where's the copper, where's the nickel? You know, you didn't ask me, but if you do want to find out, reach out, because, you know, there's 48 different elements that we've plotted in our Streamline campaign. And in September, we'll be able to also share the New South Wales data. So there's a lot of exciting things to come in this space. And I hope that everyone's connected and committed to sort of being a part of this net zero mine waste journey with us. So thank you very much. Thanks.
Thanks, everyone.
Thank you.
Thank you.
Thanks,
Thank you.
Bye.
Bye-bye.
Bye-bye.
Bye.
Thank you.
Bye.